Hello there, and welcome to Science for Sleep, where curiosity gets comfortable, difficult ideas slow down to a friendly pace, and the universe is kind enough to keep us company, while the day quietly fades behind us. Tonight, we're visiting something small, dense, ancient, and almost absurdly energetic. Its name is PSR J1748-2446 AD, which sounds less like a star and more like a password generated by a very determined telescope. Yet behind that complicated label is one of the most extraordinary objects ever found. It is a star that spins around roughly 700 times every single second. Not every minute, not every hour, not even every blink, every second. While you settle into your pillow, adjust the blanket, or stare softly at the ceiling wondering if sleep is nearby or still negotiating terms, somewhere out there this star is turning so quickly that by the time you take one slow breath, it may have spun thousands of times already. That raises a gentle and rather delightful question. What time is it where you are right now, and where in the world are you listening from tonight? Perhaps it is late evening with streetlights glowing through the curtains. Maybe dawn is beginning to gather at the edges of your window. Perhaps you're listening under headphones while the rest of the house is quiet, or from a city still humming softly outside. Wherever you are, you and I share this moment while a distant object in space keeps one of the fastest rhythms known in nature. If you find this journey soothing, interesting, or simply a pleasant place to rest your thoughts for a while, I'd be ever so grateful if you liked the video, subscribed, or returned again for another calm wander through science. It helps this quiet little corner reach other curious people who may need a softer ending to their day. Now, I should mention that a story about a star spinning 700 times per second may sound like the sort of thing that should come with sirens, dramatic music, and somebody shouting into a camera, but we will do none of that here. We will take the scenic route. We will move slowly while discussing something that refuses to do so itself. So, get comfortable, let the room grow still, and let us begin. When most of us imagine a star, we picture something like the sun. Bright, large, warm, steady. A glowing sphere hanging in space, carrying on with quiet confidence. That is understandable. The sun has been our nearest example for all of human history, and it sets expectations rather firmly. Stars, however, are a varied group. Some are larger than the sun by astonishing margins. Some are cooler and dimmer. Some live briefly and violently. Others persist for trillions of years. A few become so strange in their final stages that the word star starts to feel slightly inadequate. PSR J1748-2446 AD belongs to that strange category. It is what astronomers call a neutron star. A neutron star is what can remain after a massive star has reached the end of its normal life, run out of fuel, and collapsed under its own gravity. The outer layers may explode outward in a supernova, while the core is crushed inward with such force that matter itself is transformed. Imagine taking a mass greater than our sun and compressing much of it into an object only about the size of a city. Not a country, not a continent, a city. That means something with enormous mass packed into a sphere perhaps 20 kilometers across, give or take, depending on the exact object. It is difficult to picture because nothing in ordinary life prepares us for that kind of density. Mountains are airy by comparison. Steel is practically decorative. Even the hardest materials we know seem flimsy next to neutron star matter. A teaspoon of material from such an object, if you could somehow collect it and survive every part of that sentence, would weigh more than any kitchen scale was designed to forgive. And yet density is only part of the story. Some neutron stars spin, some spin rapidly, and a special group spin with such astonishing speed that they are called millisecond pulsars. These are neutron stars rotating hundreds of times per second, sending beams of radiation into space like lighthouse beams, sweeping across dark water. Each time the beam points toward Earth, our instruments can detect a pulse, 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 pulse. Except in this case, the pulses can come faster than thought, faster than a blink, faster than any natural rhythm we experience in daily life. PSR J1748-2446 AD is among the fastest ever found. Its measured rotation rate is around 716 times each second. In casual conversation, people often round that to 700, because even after rounding, the number remains wonderfully unreasonable. Try, for a moment, to rotate anything around you 700 times per second. A spoon would become a concern, a ceiling fan would become a legal matter, a bicycle wheel would become a memory. Yet this star does it continuously. No visible wobbling panic, no sparks of complaint, no dramatic collapse every Tuesday. Just relentless rotation, held together by gravity and the bizarre strength of matter under extreme conditions. If that sounds impossible, it helps to remember that space is where ordinary rules meet their limits. Things that seem absurd at human scale become natural under cosmic circumstances. This is one of the joys of astronomy. The universe repeatedly presents facts that sound invented. Now the name itself deserves a quick and gentle explanation. PSR usually indicates a pulsar source. J1748-2446 refers to coordinates in the sky, a map address rather than a personality. The final letters help distinguish it from other catalogued objects. Scientists need practical naming systems because the universe contains far too many things to call them all Steve. So while the name lacks poetry, the object supplies enough of its own. This star lives in a globular cluster known as Terzan 5, a dense swarm of ancient stars packed together in our galaxy. We will visit that neighbourhood properly later because it deserves attention. For now, it is enough to know that PSR J1748-2446 AD lives in a crowded stellar environment where stars gather in numbers that make our local region of space seem positively spacious. But before we travel outward, let us linger on the spinning itself. What does 700 times per second actually mean in live terms? It means that in 1 minute, the star rotates more than 40,000 times. During a short cup of tea, it may complete hundreds of thousands of rotations. During this evening's listening session, depending how long you stay with me, it could spin millions of times. You, meanwhile, may have adjusted your pillow twice. There is something charming about that contrast. We are creatures of slow scales. We walk rather than orbit. We notice seasons more than seconds. We think in mornings, meetings, meals, weekends, birthdays and years. The body has rhythms, yes, but they are modest ones. Heartbeats, breaths, steps. Then we look outward and find an object whose steady pace makes our fastest motion seem leisurely. Even hummingbird wings would look restrained by comparison. Still, speed alone does not tell the full story. What matters is that this is not merely fast. It is stable, predictable, precise. That precision is why pulsars fascinated astronomers from the moment they were discovered. Their signals can be timed with extraordinary accuracy. In some cases, pulsars rival the regularity of atomic clocks over certain intervals. They become tools for measuring gravity, testing relativity, probing interstellar gas, and searching for faint cosmic disturbances. So PSR J1748-2446 AD is not just a curiosity, it is also a laboratory, a spinning laboratory the size of a city, suspended in darkness, naturally. There is another lovely contradiction here. We often associate speed with chaos. A fast room is messy, a fast schedule is stressful, a fast machine rattles and heats and complains. Yet many cosmic systems reveal the opposite. Under the right conditions, great speed can coexist with exquisite order. Planets orbit smoothly, galaxies rotate in slow, grand structure. Pulsars flash with metronomic regularity. Nature, it seems, can be both wild and disciplined at once. And perhaps that is one reason stories like this feel comforting at night. They remind us that the universe is not random noise. It contains patterns, rhythms, structures, and dependable motions continuing whether or not we are watching. Right now, while someone somewhere folds laundry, while another person misses their bus, while a cat considers a shelf it should not leap onto, this star continues turning. It turned before tonight. It will turn after tonight. It spins through our worries with complete indifference. That may sound cold, but it can also feel strangely peaceful. Our days often seem crowded with urgent things, messages, errands, deadlines, small confusions, large confusions disguised as calendars. Then astronomy enters the room and quietly adjusts perspective. Somewhere beyond our immediate concerns is an object rotating hundreds of times per second in a cluster of ancient stars. It asks nothing of us except wonder, and wonder thankfully is restful when taken in gentle doses. Of course, once we hear about such an object, the next question arrives almost immediately. How can anything spin that fast without tearing itself apart? That question leads us into forces, momentum, collapsed matter, magnetic fields, and the dramatic life story of stars that end one existence only to begin another stranger one. Because PSR J1748-2446 AD did not start life as a tiny ultra-dense spinner. It began as a more ordinary star burning fuel in the familiar stellar way. Its current behaviour is the result of age, collapse, survival, and likely help from a nearby companion star that fed it material and sped it up over time. In other words, even the fastest known spinners may owe something to teamwork. There is comfort in that too. Nothing this remarkable appears from nowhere. It has a history. Take a slow breath for a moment and notice how still everything may seem around you right now. Perhaps you're lying in bed. Perhaps you're resting on a sofa, seated in a chair, or tucked beneath blankets that have already decided they are not moving again until morning. The room may be quiet. The furniture appears committed to permanence. The walls seem steady. The floor beneath you gives every impression of loyalty and calm. And yet, none of it is truly still. Not you, not the room, not the building, not the city, not the planet beneath your feet. Stillness, as it turns out, is often just motion we have grown comfortable enough to ignore. That is useful news for tonight's story because we are discussing a star that spins hundreds of times each second. Before we can appreciate motion at that extreme, it helps to remember that even our quietest moments are already filled with movements so familiar we barely notice it. Right now, unless you're floating in some unusual circumstance that would certainly deserve its own episode, you're being carried by Earth's rotation. Our planet turns once roughly every 24 hours. At the equator, that means the surface is moving at more than 1,600 kilometers per hour relative to Earth's axis. You may not feel like you're traveling at tremendous speed. You may feel more like you're considering whether to turn the pillow over. Both things can be true. The reason we do not notice this motion is simple. Everything around us is moving together. You, your bed, the lamp, the house, the nearby trees, the street outside, and the slightly suspicious pigeon on the roof are all sharing the same ride. Motion is easiest to notice when something changes relative to you. If everything moves together smoothly, the sensation disappears into normality. This is why passengers on a steady airplane can sip water, read a book, or wonder why the snack is always smaller than expected. They are moving quickly through the sky, but because cabin, seat, air and body are moving together at nearly constant speed, it feels calm. Only when the plane turns, accelerates, slows or bumps do we notice. Our senses are less interested in motion itself than in changes of motion. That distinction matters. Humans evolved to detect what shifts, approaches, stumbles, lunges, rolls, or suddenly behaves like a problem. Constant smooth movement tends to fade into the background. Sudden movement receives immediate attention. A branch snaps, a door closes, a mug tips. The nervous system becomes very alert. But the Earth spinning through space, We have outsourced concern, and Earth's rotation is only the beginning. While it turns, Earth also orbits the Sun at roughly 30 kilometers every second. Every second of your life, you travel farther around the Sun than many people drive in an entire day. Meanwhile, the Sun itself moves through the Milky Way galaxy, and the galaxy moves through the wider cosmos. So if you ever feel that you have not gone anywhere lately, astronomy would like a word. Even during your most stationary afternoon, you have been moving magnificently. This creates a delightful paradox. We often divide life into moving and not moving, busy and resting, travelling and staying home. Physics is less sentimental about categories. From that perspective, rest is usually local and temporary. Motion is layered, relative, and everywhere. Consider sitting in a parked car. To you, the seat is still. To someone walking past, you're stationary relative to the road. To the moon, you are rotating with Earth. To the Sun, you are orbiting. To the centre of the galaxy, you are tracing a far grander path. Which description is correct? All of them. That is one of the gentlest mind benders in science. Motion depends on the frame from which you describe it. There is no universal sticker labelled truly still attached to ordinary objects. Even the phrase "I'm not moving" usually means I'm not moving much relative to the thing I care about right now. That thing might be the room, the road, the train platform, or the person trying to take a photo. This is why motion can feel mysterious in daily life. We experience one scale at a time. The body notices footsteps, swaying, turning, acceleration. It does not naturally report orbital mechanics over breakfast. Our inner senses are practical, not cosmic. Inside your ears are structures that help detect balance and acceleration. They are excellent at telling you when you spin in a chair too enthusiastically and regret your choices. They are less concerned with the Earth's stable rotation, because that motion is smooth and constant. The body says, "Nothing urgent here," and so consciousness gets on with other matters. Stillness, then, is partly a negotiated perception. If motion is smooth enough, constant enough, and shared enough, it feels like stillness. That idea becomes especially useful when imagining PSR J1748-2446 AD, the neutron star spinning around 700 times every second. At first glance, that number sounds impossible because we compare it to our own scales. We imagine ourselves on the surface of something turning so quickly and immediately begin filing complaints. But stars do not use human scales. Objects in the universe obey size, mass, gravity, momentum, and structure. A tiny dense star can behave in ways a sofa cannot, thankfully. Imagine a playground merry-go-round. Near the centre, motion feels manageable. Near the edge, the ride becomes much more dramatic. Distance from the axis matters. Speed at the rim depends on how fast the platform rotates and how far you are from the middle. Now imagine shrinking the whole system dramatically. A neutron star is small compared with ordinary stars, roughly city-sized. Compact dimensions allow astonishing rotation rates while remaining physically possible under extreme conditions. So when we hear 700 times per second, we should not picture a giant bloated star whirling like a tossed beach ball. We should picture something dense, compact, and built by gravity into one of nature's strangest machines. Still, before we rush back to neutron stars, let us stay with familiar motion a little longer, because our own lives are full of unnoticed examples. Have you ever sat on a train at a station and briefly thought your train was moving, only to realise the train beside you had started to roll instead? For a moment, the brain becomes uncertain which frame to trust. Window, platform, seat, neighbouring carriage. Without clear reference points, motion can be surprisingly ambiguous. You may feel movement where none exists, or miss movement that absolutely does. The same happens on escalators after stepping off them. The body expects continued motion for a beat. Or on boats, where land may seem to sway afterward. The brain continuously predicts movement and updates those predictions from incoming signals. We do not merely sense motion, we interpret it. That interpretation can be fooled. Anyone who has spun in circles as a child knows this well. Stop suddenly, and the room seems to continue rotating. Fluids in the inner ear keep moving briefly, sending signals that no longer match the eyes. Result: confusion, laughter, questionable walking. The universe remains blameless. Motion also shapes time perception. Long car journeys can feel slow while lived and short in memory. Holidays often feel brief in the moment, yet rich afterward. Waiting in a queue can make seconds stretch into philosophical territory. Part of that comes from attention. When we monitor progress closely, motion feels slower. When absorbed, it vanishes. Watch a kettle. It delays. Forget the kettle. It surprises you. The same can happen on treadmills. Legs work hard. Scenery refuses to cooperate. The body feels effort without satisfying displacement. Some people find this efficient. Others find it a mild insult. Our emotional relationship with motion is equally varied. Gentle rocking can soothe infants and adults alike. Rhythmic movement often calms the nervous system. Trains, rain on windows, ship cabins, and slow drives at night can create drowsiness through repetitive motion and sound. Meanwhile, sudden jerks, drops, or sharp turns do the opposite. The body becomes alert. Again, it is not motion itself, but change, unpredictability, and interpretation that matter most. This helps explain why the image of a rapidly spinning star can be exciting to think about, while the actual object may be astonishingly stable. Pulsars rotate with immense regularity. Their motion is not chaotic flailing, it is disciplined repetition. That difference is important. We sometimes imagine speed as frantic because human speed often is. Running late is frantic. Typing after forgetting a deadline is frantic. Looking for keys while already wearing stress as a hat is frantic. But nature can do speed quietly. Electrons move, planets orbit, stars rotate, galaxies drift. No panic required. There is another layer of stillness worth mentioning tonight: internal motion. Even if you are lying perfectly still, your body is active. Blood moves through vessels, lungs expand and release, nerves fire, cells repair damage. Chemical reactions unfold by the countless trillions. Proteins fold, molecules collide, heat spreads. Resting does not mean inactive, it means coordinated. Life is organized motion. That may be comforting if you ever worry that you're doing nothing. Often the most important processes happen while outwardly still. Healing, digestion, memory consolidation, emotional settling, sleep itself. The body knows productive quiet. Stars do too, in their own way. Even a calm-looking star is the site of enormous internal activity. Fusion, convection, radiation, pressure balances, magnetic behavior. Surface serenity can hide magnificent labor. The same universe that gives us spinning neutron stars also gives us the lesson that appearances of stillness can be incomplete descriptions. A mountain seems fixed, yet continents move. A forest seems quiet, yet roots trade signals underground. A sleeping person seems inactive, yet the brain may be sorting entire days. A dark point in space may be rotating hundreds of times each second. Science repeatedly invites humility about surfaces. Now, if everything moves, one might ask whether stillness means anything at all. It does. Stillness remains meaningful within context. Relative to your room, you may be still. Relative to the bed, still. Relative to the person beside you trying not to disturb you, hopefully still enough. Context gives motion usefulness. Without agreed frames of reference, life becomes awkward quickly. Imagine asking someone to hold still for a photograph and they reply, relative to the galactic center, impossible. Technically interesting, socially difficult. So we use practical frames, streets, rooms, tables, timetables. Human life runs on nearby reference points, while physics keeps the larger ledger in the background. and that balance may be wise. If we felt every cosmic motion all the time, grocery shopping would become overwhelming. Instead, we receive a manageable version of reality scaled to survival and comfort. Then, when curiosity arrives at night, we can widen the lens. Right now you may feel at rest, yet you are on a rotating world orbiting a star moving through a galaxy in an expanding universe. Your body itself is alive with patterned motion. Even thoughts are dynamic events across networks of cells. Stillness has never been the absence of motion. Often, it is harmony within motion. That idea carries us beautifully toward PSR J1748-2446 AD, because what seems shocking at first, a star spinning 700 times each second, becomes less alien once we remember that motion is everywhere. Scales differ, and nature is comfortable with speeds far beyond our instincts. The real question is not whether the universe permits such movement. Clearly it does. The deeper question is how an ordinary star could ever become something so compact and so fast. Now that we have gently reminded ourselves that motion can hide inside apparent stillness, we are ready to properly meet the object at the centre of tonight's journey. Its name is PSR J1748-2446 AD. Not the sort of name that rolls gracefully off the tongue, not the sort of name likely to appear on a souvenir mug, and yet behind that catalogue label sits one of the most astonishing stars ever discovered. This is a neutron star spinning around 716 times every second, commonly rounded in conversation to 700 because the exact number is impressive enough without insisting on every decimal place of astonishment. To understand what that means, imagine snapping your fingers once. During that tiny interval, this star may have rotated dozens of times. Blink naturally without rushing. It may have turned well over 100 times before your eyes reopen. Take one slow breath in, then out. Thousands of rotations. While we live among heartbeats and footsteps, PSR J1748-2446 AD keeps time in a rhythm almost beyond intuition. And yet it exists quite calmly, many thousands of light years away, turning in darkness with the steady confidence of something that has no interest in our disbelief. The letters at the beginning of its name, PSR, stand for Pulsar. That tells astronomers what kind of object it is. A pulsar is a rapidly rotating neutron star that emits beams of radiation from its magnetic poles. As the star spins, those beams sweep through space. If Earth happens to lie in the path of that sweep, our telescopes detect repeated pulses. Pulse, 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 except in this case so rapidly that the pulses arrive hundreds of times each second. The remainder of the name is essentially an address in the sky. J1748-2446 refers to coordinates, helping scientists locate it precisely. The final letters distinguish it from other nearby sources because the universe has been rather extravagant with objects. So although the name sounds technical, it is simply practical. Scientists needed a filing system. The cosmos did not volunteer nicknames. If it had, perhaps this one might have been called the Relentless Spinner, the city-sized whirlwind, or that ridiculous thing in Terzan 5. But PSR J1748-2446 AD it is. It was discovered in 2004 by astronomers using radio observations, and its extraordinary spin rate quickly made it famous in the quiet, excited way astronomy does fame. No red carpets, no shouting headlines in every household, just researchers around the world looking at data and saying with admirable restraint, "Good heavens." At the time of discovery, it became the fastest spinning known neutron star, a record it has continued to hold among confirmed observations for many years. There may be faster objects waiting to be found. The universe enjoys surprises. But as of what we know, this star remains one of the champions of rotation. Now, when people hear fastest known spinner, they often picture something blazing around wildly, perhaps glowing furiously, shedding sparks like an overworked carnival ride. That is understandable, but not accurate. PSR J1748-2446 AD is not chaotic. It is precise. That may be the most surprising part. Its spin is measurable because it is regular, predictable, stable enough for astronomers to count pulses and determine the rotation rate with remarkable confidence. In many ways, pulsars behave like cosmic clocks. Strange clocks, certainly. Compact clocks with crushing gravity and intense magnetic fields. But clocks nonetheless. There is something soothing in that thought. Far away in space, an object of extreme physics keeps a steady beat. Not for us. Not because it intends to. Simply because nature, under the right conditions, produces order in places we least expect it. To appreciate the scale of this object, let us speak briefly about size. PSR J1748-2446 AD is a neutron star. That means it likely contains more mass than our Sun, packed into a sphere only around the size of a city, perhaps 20 kilometers across or thereabouts, depending on the exact equation of state and model estimates. If you place something with solar-scale mass into a volume that small, ordinary language begins to lose traction, density becomes immense, gravity becomes fierce, matter behaves in forms unfamiliar to everyday experience, and because the star is compact, it can rotate astonishingly quickly without immediately flying apart. A giant fluffy star spinning 700 times per second would be a dramatic and short-lived misunderstanding. A dense neutron star is another matter entirely. Think of a figure skater pulling in their arms during a spin. As they become more compact, rotation speeds up. We will explore that process more fully later, but it helps here. Nature often rewards compactness with speed. PSR J1748-2446 AD is compactness taken to an extreme. It lives in a place called Terzan 5, a globular cluster near the centre region of the Milky Way. Globular clusters are ancient swarms of stars packed closely together, like crowded celestial cities. While our Sun has generous personal space by stellar standards, stars in globular clusters can exist in much tighter neighbourhoods. That matters because close stellar environments create opportunities for encounters, binary systems and the recycling processes that can spin neutron stars up to extreme rates. In other words, this star did not become extraordinary in isolation. Its environment likely played a role. Even cosmic records sometimes require helpful neighbours. Terzan 5 itself is a fascinating place. Dense, old, rich in stars, and home to many exotic objects. If the Milky Way were a vast landscape, globular clusters would be ancient stone citadels hanging in orbit around it. They preserve old populations of stars and create conditions where rare systems can form more readily than in quieter regions. So it is fitting that one of the universe's great spinners resides in such a crowded district. Now let us pause on the number again, 716 rotations per second. Numbers that large can become abstract quickly, so let us anchor it gently. A hummingbird may flap wings dozens of times each second. A household fan might rotate several times each second depending on speed. A blender can spin thousands of revolutions per minute. PSR J1748-2446 AD performs hundreds of full rotations each second. Not minute. Second. By the time you finish reading this sentence in your mind, it has spun many thousands of times, and unlike a kitchen appliance, it requires no plug socket, no user manual, and no warning label translated into 12 languages. It is powered by physics and history. Its present state tells the story of a much earlier star that lived, exhausted its fuel, collapsed, survived as a neutron star, and then likely gained matter from a companion that spun it up further over time. So when we meet PSR J1748-2446 AD, we are not meeting a simple object. We are meeting the result of multiple cosmic chapters already lived. Birth, fuel burning, death of one form, rebirth in another, accretion, acceleration, persistence. That long biography now expresses itself as rhythm. There is also a subtle human lesson in how such discoveries happen. No one simply looked through a backyard telescope and announced, "Ah yes, there is the 700 times per second star." Objects like this are found through patient observation, instrumentation, signal analysis, mathematics, and repeated checking. Radio telescopes gather faint data. Scientists sift patterns from noise. Measurements are refined. Discovery often sounds dramatic after the fact, but in practice it is usually built from careful work. A great many wonders enter human awareness quietly. This one arrived through radio pulses crossing space for thousands of years, until instruments and minds on Earth became ready to notice them. That is a lovely thought. The signal existed before the discovery. The universe was already speaking. We had to learn how to listen. There is another reason PSR J1748-2446 AD matters beyond its record-setting speed. Extreme objects help test the boundaries of physics. The faster a neutron star spins, the more scientists can learn about internal structure, mass limits, magnetic effects, and the behavior of matter under crushing density. How fast can a neutron star rotate before breaking apart? What does that limit reveal about matter packed beyond atomic norms? How do magnetic fields behave in such systems? How does a binary companion transfer enough material to produce these rates? A record holder is not merely impressive, it is informative. Nature places signposts at the edges of possibility. Scientists study them to understand the rules, and yet, for all this importance, there is something almost humorous about the contrast between its complexity and our sleepy conversation tonight. Somewhere in a dense star cluster, a compact remnant rotates hundreds of times per second under conditions of staggering gravity. Meanwhile, here on Earth, one of us may be deciding whether to stretch 1 foot outside the blanket and risk the consequences. Both are real events in the same universe. That coexistence is part of what makes astronomy charming. It never demands we stop being human in order to appreciate the cosmic. We can admire neutron stars while misplacing our glasses. Now, if you could somehow approach PSR J1748-2446 AD safely, which you absolutely cannot and should not attempt with current travel options, you would encounter an environment unlike anything familiar. Gravity near the surface would be immense, magnetic fields severe, radiation dangerous, surface conditions extreme. This is not a holiday destination. It is, however, a magnificent reminder that stars do not all age quietly into obscurity. Some become compact engines of motion. The fastest known spinner among them invites us to widen our expectations of what a star can be. Because once upon a time, stars were simple lights in the sky. Then they became suns, then furnaces, then evolving systems, then collapsed remnants, then pulsars, then clocks, then laboratories, and with PSR J1748-2446 AD, a star also became a benchmark for rotational extremes. Of course, hearing that title naturally leads to another question. What does 716 times each second truly feel like in physical terms? How fast would the surface move? How different is that from anything we know? What happens to matter forced into such relentless rotation? Now that we have properly met PSR J1748-2446 AD, it is time to sit quietly with the number itself, 700 times per second, or more precisely, around 716 rotations each second, though tonight we're allowing ourselves the rounded version because the rounded version is already unreasonable enough. The human mind has an interesting habit with large numbers. At first they feel dramatic, then, after a moment, they become blurry. We hear them, nod politely, and continue as though we fully understand, but many numbers only reveal their true character when translated into experience, so let us do that gently. What does it actually mean for a star to spin 700 times every second? First, consider 1 second. A second is short but familiar. It is the pause between 2 ticks on a clock. It is the time it takes to blink. It is the tiny interval in which you can decide to turn over in bed and then somehow take much longer than expected to do so. Within that single second, PSR J1748-2446 AD rotates hundreds of full times, not wobbles, not partial turns, full rotations. Imagine standing beside a wheel and trying to count its turns. 1, 2, 3, 4. You would lose track almost instantly. At 700 per second, counting becomes surrender. By the time you say the word 1, the star has likely completed more spins than your sentence has letters. Now stretch that to a minute. 1 minute contains 60 seconds. Multiply that by roughly 700 rotations, and you arrive at more than 40,000 spins in 1 minute. 40,000. That is enough turns to make most household machinery file formal objections. In 10 minutes, hundreds of thousands. In an hour, millions. During a normal night's sleep, it may rotate tens of millions of times, while you drift through dreams involving misplaced trains or surprisingly emotional sandwiches. This is one of the charms of astronomy. While we experience time through moods and schedules, the universe keeps entirely different rhythms in the background. Still, raw counting only takes us so far. Let us ask a better question. How fast is the surface moving? Because rotation is not just about how often something turns. It is also about how quickly points on that object travel around the circumference. Think of a carousel. The center moves little. The edge moves much more. The farther from the axis, the faster you travel during each turn. PSR J1748-2446 AD is small compared with normal stars, likely around 20 kilometers across, give or take estimates. That compact size matters enormously. A neutron star is roughly city-sized, not sun-sized. Even so, the surface at the equator is moving at a remarkable fraction of the speed of light. Depending on the exact radius used, the equatorial speed can be around a quarter of light speed, sometimes estimated in that general range. That means tens of thousands of kilometers every second. To compare, a passenger jet moves at roughly hundreds of kilometers per hour. Earth orbits the Sun at around 30 kilometers per second. This star's surface can move vastly faster than anything in ordinary human transport, and at speeds where relativity is no longer just a textbook guest appearance. If you tried to commute there, the travel insurance form would become complicated. Now, when we hear surface, we should be careful not to imagine a peaceful rocky crust with benches and scenic overlooks. A neutron star surface is an extreme environment. Gravity is crushing, matter is exotic, magnetic fields can be intense, radiation can be dangerous. This is not somewhere one strolls, yet the concept of a surface moving at such speed helps make the number tangible. We are not merely discussing abstract spins, we are discussing matter racing around a compact object at astonishing velocity, and it does so steadily. That steadiness may be more impressive than the speed itself. Many things can move fast briefly. A tennis ball can be struck hard. A race car can accelerate. A sneeze can surprise everyone nearby. But maintaining extraordinary speed with regularity over long timescales is different. That requires balance, structure, and physical conditions that permit endurance. PSR J1748-2446 AD is not performing a stunt. It is living that way. Let us compare this to familiar rotations. Earth spins once every 24 hours. Jupiter, famous for rapid planetary spinning, rotates roughly once every 10 hours. A kitchen blender might rotate many thousands of times per minute, depending on setting and courage. A dentist's drill, let us acknowledge respectfully from a distance, can rotate far faster still. But stars are not kitchen tools, and planets are not neutron stars. What makes PSR J1748-2446 AD special is the combination of stellar mass, compact size, and extraordinary rotational rate. It is a collapsed star behaving with the rotational tempo of machinery. That contrast is what captures the imagination. A star should feel grand, slow, majestic. This one behaves like precision hardware built by gravity. There's also a useful distinction between speed and acceleration. Something spinning fast does not necessarily feel strange if already in steady rotation. What matters physically for forces felt at the surface is the centripetal acceleration needed to keep matter moving in circles, and here the numbers become intense. Matter at the equator constantly wants, in a loose-speaking sense, to move straight ahead due to inertia. Gravity and internal forces keep it bound to the star. The faster the spin, the more dramatic that contest becomes. So when scientists ask how fast a neutron star can spin, they are really asking when rotation begins to challenge structural survival. At some point, spin becomes too much, and matter near the equator could begin to escape, or the star could become unstable. PSR J1748-2446 AD lives close enough to those boundaries to be scientifically exciting. It tells us something about where the limits may lie. Nature often reveals itself best near extremes. The coldest places teach thermodynamics. The brightest explosions teach stellar death. The fastest spinners teach dense matter physics. Now let us bring this back to human intuition, because large cosmic facts are best enjoyed when tied to small familiar moments. Tap your finger lightly once on a table or blanket. That little tap may take a fraction of a second. During it, the star has already turned dozens or hundreds of times. Take a sip of water, thousands of spins. Check your phone and pretend it was only for the time, many thousands. Say aloud, "I should really be sleeping." Enough rotations have passed to make the point dramatically. The star's rhythm is so fast that our own actions become geological by comparison. Yet there is no need to feel outpaced. Humans are built for other tempos. We notice seasons, stories, relationships, and tea cooling. We were never meant to compete with pulsars, and perhaps that is fortunate. Imagine trying to maintain friendships at neutron star scheduling speeds. Sorry I missed your call. It has been 12 million rotations. There is another fascinating layer here, sound. If we convert pulsar pulses into audible frequencies, some fall into ranges we can hear, or into rhythmic patterns we can interpret as sound. A star rotating hundreds of times each second corresponds to a frequency in the neighborhood of hundreds of hertz. That means if translated properly, its beat could resemble a low mechanical hum or tone. So the universe contains objects whose spin can be rendered as something like audible rhythm. A star can, in a sense, be listened to. That thought feels surprisingly intimate. Far away, something impossible seeming turns with such regularity that we can convert its pulses into sound, and sit here quietly hearing the heartbeat of collapsed matter. Of course, the number also reminds us how misleading scale can be. If a giant ordinary star tried to rotate 700 times each second, it would be a disaster. Outer layers would fling outward. Stability would fail. The size alone would forbid it. But compress mass into a tiny neutron star, and suddenly such speeds become possible. This is one of the recurring lessons of science. Change the scale. Change the rules that dominate. At insect scale, surface tension matters. At mountain scale, geology matters. At neutron star scale, density and relativity enter the room. And they do not come quietly. You might wonder whether the star is slowing down. Yes, pulsars generally lose rotational energy over time, often gradually slowing as they emit radiation and particles. But some are recycled by companion stars feeding them matter, spinning them back up. We will visit that remarkable process soon. For now, it is enough to know that 700 times per second is not necessarily how the story began. It may be the result of long cosmic history, not youthful recklessness. even stars with outrageous habits often have backstories. Another useful comparison is Earth's day. Our world rotates once in 24 hours. We organise life around that pace: sunrise, afternoon, evening, sleep. PSR J1748-2446 AD experiences the equivalent of 700 days every second if one foolishly defines a day as one rotation. That would make calendars awkward. Happy birthday, you're approximately 22 billion days old. Best to keep our current system. Still, there is something calming about contemplating a rhythm so different from ours. It reminds us that time is experienced through process. For Earth, a day is rotation. For us, it is activity and light. For a pulsar, rotation is simply identity. Its spin is not hurried, it is just what it is. We often associate fast with stress because human speed usually arrives with deadlines. Running late, speaking quickly, multitasking poorly, pretending to remember passwords. But cosmic speed has no anxiety attached. The pulsar is not in a rush. It is not trying to finish anything before midnight. It spins because physical laws and prior history made it so. That can be oddly comforting. Speed does not always mean strain. Sometimes it means equilibrium at a scale unlike our own. And if tonight's number still feels too strange to grasp fully, that is perfectly fine. Some facts are not meant to fit neatly into instinct. They are meant to stretch it. 700 times per second is one of those facts. It asks the mind to widen. It invites humility. It reminds us that reality can exceed imagination while remaining completely real. Naturally, once we understand the speed a little better, the next question arrives almost immediately. How does an ordinary star end up as a compact object capable of such motion in the first place? Long before PSR J1748-2446 AD became a city-sized object spinning hundreds of times each second, it was something far more familiar. It was a star, not yet crushed into extraordinary density, not yet flashing radio pulses across space, not yet a record holder in the quiet halls of astrophysics. It likely began as a more ordinary stellar body, formed in a cloud of gas, gathering mass slowly, igniting deep internal fire and entering the long middle stretch of a star's life where gravity and energy learn to live in balance. That may be one of the most useful truths in astronomy. Many of the strangest objects in the universe begin in very ordinary ways. A butterfly starts as something less glamorous. An oak begins as an acorn. A neutron star begins as a star trying to mind its own business. When we look at the night sky, stars often appear similar from Earth. Tiny points of light, some brighter, some dimmer, some tinted faintly red or blue. Yet each one is a physical place with its own mass, chemistry, age, history, and future. Some are small and patient. Some are large and reckless. Some will fade quietly. Others will end in violence visible across galaxies. The fate of a star depends mostly on one thing: mass. Mass determines how strongly gravity squeezes inward. Gravity determines pressure in the core. Pressure determines temperature. Temperature determines how quickly nuclear fusion proceeds. And fusion determines how long a star can maintain the delicate balance between collapse and outward energy flow. Stars, in a sense, spend most of their lives negotiating with gravity. Gravity pulls inward relentlessly. Fusion pushes outward by heating the interior and generating pressure. As long as those two influences remain in rough equilibrium, a star can remain stable for immense periods of time. Our Sun is in such a phase right now. It has been calmly fusing hydrogen into helium for billions of years and expects to continue for billions more. Dependable, warm, and occasionally responsible for sunburn, it is a fine example of a middle-aged star with routine habits. But not all stars are so measured. The progenitor of PSR J1748-2446 AD was likely more massive than the Sun. Massive enough that its life would be shorter, brighter, and more intense. Large stars burn fuel rapidly. They live extravagantly. If small stars are careful candle flames, massive stars are bonfires using tomorrow's wood today. This is because more mass means stronger inward gravity. Stronger gravity compresses the core more intensely. Greater compression raises temperature and pressure. Fusion reactions accelerate. The star shines more brilliantly, but pays for that brilliance with speed. Nature often offers this trade. Brighter can mean shorter, larger can mean faster, more dramatic can mean less durable. So somewhere in a dense region of ancient stars, perhaps within what would become the environment of Terzan 5, gas and dust once gathered under gravity. Clouds collapsed into knots. Knots became protostars. Matter spiraled inward, heated and compacted. Eventually, one growing star crossed the threshold where core temperatures became high enough for hydrogen fusion to ignite. That moment is, in a sense, stellar adulthood. A star is born not when gas first gathers, but when it lights itself from within. From then on, its life is powered by fusion. Hydrogen nuclei combine into helium, releasing energy according to the famous relationship between mass and energy. Tiny amounts of mass become tremendous energy. That energy moves outward through radiation and convection, eventually escaping as starlight. Every warm morning on Earth is evidence of this process in another star. Every distant glimmer in the night is the same principle in many forms. The early life of PSR J1748-2446 AD's ancestor may have looked almost ordinary by cosmic standards. It shone. It balanced gravity. It likely rotated, as most stars do, though far more modestly than the neutron star it would later become. It may have had neighbouring stars nearby. It may have belonged to a binary system even then. It lived through ages beyond human imagination while no eyes existed to watch. That is another gentle feature of the universe. Most important events happen unobserved. Stars form without applause. Galaxies merge without headlines. Planets cool in silence. Only much later do curious beings arrive and reconstruct the story. During the long, stable phase of a star's life, the core slowly changes composition. Hydrogen decreases. Helium ash accumulates. Gravity presses inward more strongly as the easy fuel thins. Eventually, the balance that sustained the star begins to shift. For stars like the Sun, later life becomes swollen and red, then calmer and quieter in death. But for sufficiently massive stars, the ending is more severe. Once hydrogen in the core is exhausted, the core contracts and heats further. New fusion stages begin. Helium can fuse into heavier elements. In larger stars, this process continues in layers: carbon, neon, oxygen, silicon, and onward. The star develops a kind of onion-like structure with shells of fusion around the centre. This sounds organised, and in one sense it is. But it is also the prelude to instability. Each new fuel stage burns faster than the last. Hydrogen burning can last millions or billions of years. Later stages may last thousands, years, days, or less, depending on mass and conditions. The final acts hurry. A star that once seemed timeless begins spending fuel with urgency. Why stop at heavier elements? Because iron changes the rules. Fusion up to iron can release energy. Fusing iron into heavier nuclei does not provide the same support. Instead of helping resist gravity, it becomes energetically unfavourable in the core context of a massive star. Once enough iron accumulates, the star loses its best defence. Gravity notices immediately. Imagine a grand building whose central supports have quietly weakened. For years it stood balanced. Then suddenly the load can no longer be carried. Collapse begins. And collapse in a massive star is not gentle. The core falls inward at extraordinary speed. Temperatures soar. Densities rise catastrophically. Electrons and protons are forced together, creating neutrons and neutrinos in enormous numbers. Matter transforms. The inner core stiffens suddenly when nuclear densities are reached, and in falling outer layers can rebound or be driven outward in the titanic event we call a supernova. For a brief time, the star may outshine entire galaxies. then what remains is not the former star. Its outer identity has been blasted away. Its inner core survives in altered form. If the remaining core mass is within the right range, it becomes a neutron star. That is likely the turning point relevant to our story. The ordinary star ends. Something extreme begins. Now it is worth pausing to appreciate how complete this transformation is. A normal star is large, diffuse by comparison, powered by fusion, and luminous through ongoing nuclear reactions. A neutron star is tiny, incredibly dense, no longer powered like a normal star, and supported by quantum pressures and nuclear matter effects rather than ordinary gas pressure. It is as though a mountain-sized orchestra collapsed into a tuning fork the size of a city. Same matter lineage, entirely different behaviour, and yet continuity remains. Angular momentum, magnetic fields, mass history, binary relationships and composition all carry traces of what came before. The neutron star is not unrelated to the original star. It is its remnant compressed biography made physical. This helps explain why some neutron stars spin rapidly. If the parent star rotated, even modestly, collapse to a far smaller radius can dramatically increase spin rate through conservation of angular momentum. The same principle explains why a skater spins faster by pulling arms inward. A huge star rotating slowly can become a tiny remnant rotating quickly. Later, if a companion star feeds material onto it, that spin can increase even further. So the extreme object does not emerge from nowhere. It inherits and amplifies history. That is true in many systems, not just stars. Pressure reveals structure. Compression magnifies tendencies. What was subtle can become dominant. There is also something humbling in how little separates the familiar from the extraordinary. The atoms in your body were forged in stars. The iron in blood traces ancient stellar processes. The oxygen you breathe owes itself to generations of stars living and dying before Earth existed. The difference between a calm daylight star and a neutron star is not different laws of reality. It is the same universe under different conditions. Change the mass, change the age, change the balance of forces. Reality reveals a new face. If one could have visited the earlier star in its stable era, it might not have seemed destined for fame. It would have been one among many stars burning steadily. Nothing in the quiet light would clearly announce, "One day I shall become a pulsar rotating 700 times per second." That uncertainty mirrors life in smaller ways. Many remarkable outcomes begin invisibly. Seeds do not advertise forests. Children do not announce biographies. Ordinary phases often conceal dramatic futures. Astronomy is full of delayed surprises. Of course, not every massive star becomes the fastest known spinner. Many factors intervene: mass loss through stellar winds, binary interactions, supernova asymmetries, magnetic braking, accretion history, environment, timing, companions, chance, within lawful boundaries. PSR J1748-2446 AD likely required a specific sequence of events: survive collapse as a neutron star, remain in or acquire a binary system, receive matter from a companion over long periods, gain angular momentum, become what astronomers call a recycled millisecond pulsar. That phrase may sound technical, but it carries a simple idea. An old compact star given renewed spin by its neighbour. Even among exotic objects, relationships matter. The notion of recycling in space is also oddly charming. On Earth, we recycle paper, glass, and cans. In globular clusters, the universe recycles neutron stars into precision rotators. Standards differ. There is another emotional comfort hidden in stellar evolution. Endings are often transformations rather than erasures. The original star no longer exists in its first form. Its outer layers were expelled. Its fusion life ended. Yet its core persists as something new, denser, stranger, and in some respects more useful scientifically than before. The story continues through altered identity. Nature does this often. Cloud becomes rain, wood becomes flame and ash, star becomes remnant. Nothing stays fixed, but much continues. Now imagine the timescales involved. Millions of years of burning, gradual internal changes, final collapse in seconds. After ages of stability, transformation can happen suddenly. That too is common in complex systems. Slow preparation, fast transition, water warms slowly, then boils. Stress accumulates, then releases. Stars age for eons, then collapse. And after collapse, a neutron star remains, spinning, cooling, radiating, waiting perhaps for the next phase of its story. For PSR J1748-2446 AD, that next phase likely involved a nearby companion star transferring matter. Material spiraled inward, bringing angular momentum with it, steadily accelerating the neutron star over immense spans of time until it became one of the fastest known rotators in the galaxy. So when we admire the current object, we are seeing not one event, but layers of events stacked through time. Birth cloud, main sequence life, fuel exhaustion, collapse, explosion, survival, binary feeding, acceleration, precision. The present state is history made visible. That may be why astronomy feels so rich at night. Every point of light can contain chapters written across timescales beyond instinct. We look upward and see stillness, but hidden inside are long stories of pressure, motion, change, and reinvention. PSRJ 1748-2446 AD is one of those stories condensed into a compact spinning remnant, and once an ordinary star has collapsed into something so dense, the next question becomes unavoidable. What does matter itself become when gravity crushes it that far? There comes a point in the life of some stars when the long arrangement can no longer continue. For millions of years, sometimes far longer, a star lives by balance. Gravity presses inward from every direction. Heat and pressure generated by fusion push outward. Neither side fully wins. The result is stability, or at least the star's version of it. Light pours outward. Layers remain supported. The star keeps its shape. From far away it looks calm, dependable, almost permanent. But permanence is often just a slow countdown wearing good manners. Inside a massive star, fuel is not infinite. The core changes gradually through long eras of burning. Hydrogen becomes helium. Later, helium becomes heavier elements. Then heavier fuels ignite in sequence, each stage shorter than the last. What once lasted millions of years may be followed by phases lasting thousands, then years, then days, and eventually less. The star that seemed patient begins living faster. This is one of the hidden dramas of astronomy. A bright object in the sky can appear unchanged for ages, while deep inside, the timetable accelerates. The outer layers may still glow serenely. The core may already be in trouble. Tonight we arrive at the instant when trouble becomes destiny. To understand stellar collapse, imagine a great cathedral supported from within by furnaces. As long as the furnaces burn hot enough, the walls hold against inward pressure. If the fires weaken, support fails. The structure does not politely ask for extra time, it falls. That comparison is imperfect, but useful. In a massive star, the supporting fire is fusion. As long as fusion releases enough energy, pressure resists gravity. Yet each new stage of fusion creates ash, changes composition, and moves the star closer to a difficult limit. Eventually the core becomes rich in iron. Iron is the turning point. For lighter elements, fusion can release energy and help support the star. Iron does not offer the same bargain under stellar core conditions. Fusing iron into heavier nuclei does not provide the outward rescue the star needs. Instead of generating useful pressure, the process becomes energetically costly. The star has reached fuel that cannot save it. Gravity has been waiting. What happens next occurs with astonishing speed. The The core, no longer adequately supported, begins to collapse inward. Matter that once held position starts falling toward the centre. Temperatures soar, densities climb. The collapse accelerates because stronger compression means stronger gravity and fewer remaining defences. Imagine an elevator whose cables have snapped, except the elevator is a star's core and the shaft leads into conditions beyond ordinary matter. Within moments, electrons are forced into protons. Under immense pressure, they combine to form neutrons and release neutrinos. This process, called electron capture, changes the nature of the material itself. Atoms as we know them begin to disappear. The familiar structure of matter with nuclei orbited by electrons cannot survive such compression. Empty space inside atoms is squeezed away. Electrons lose their independent arrangement. The core becomes something far stranger and denser. This is one of the reasons neutron stars are so extraordinary. They are not made of ordinary matter arranged unusually. They are matter pushed into a regime where ordinary categories fail. Meanwhile, the collapse continues inward at a substantial fraction of light speed in some regions. Entire layers rush toward the centre. Temperatures rise into billions of degrees. Neutrinos flood outward in unimaginable numbers, carrying vast energy. If you have ever seen an object suddenly crumple after hidden weakness gave way, you have witnessed a tiny, gentle cousin of this principle. Long preparation, rapid transition. Then, deep in the collapsing core, density reaches nuclear levels. Matter resists further compression much more strongly. The inner core stiffens abruptly. Infalling material slams into that resistance. A rebound forms. Shock waves emerge. Now we approach the event most people know by name, supernova. The outer parts of the star, which had been falling inward, can be blasted outward in one of the most powerful explosions in nature. Exactly how the shock is revived and sustained involves complex physics, neutrino transport, turbulence, asymmetry, and ongoing detailed study. Stars do not owe us simple endings, but the broad story remains clear. A massive star's core collapses. The star's outer layers are violently expelled. What remains at the centre depends on mass. If the remnant core is too heavy, collapse may continue toward a black hole. If the remaining mass lies in the right range, the core stabilizes as a neutron star. For PSR J1748-2446 AD, this latter path is likely what happened. The ordinary star ended. A neutron star was born. That sentence sounds neat and tidy. Reality was not. Think of the violence involved. A star many times the mass of the Sun suffers catastrophic internal failure. Matter plunges inward. Nuclear forces push back. Shock waves race outward. Neutrinos stream through surrounding layers. Vast shells of material are hurled into space. Yet from that chaos emerges an object only tens of kilometers across. Compact, dense, spinning, still there. This contrast between explosive birth and stable remnant is one of the recurring wonders of astrophysics. Some of the universe's most precise objects are created in catastrophic events. Pulsars, famous for regular timing, are born from stellar disaster. There is something oddly familiar in that pattern. Stability often follows upheaval. New forms emerge after breakdown. Systems reorganize under pressure. The universe appears comfortable with reinvention. Let us slow down and consider scale again. Our Sun contains nearly all the mass of the solar system. If compressed into a neutron star, much of that mass could fit inside an object around city size. That means a tremendous amount of matter packed into a tiny radius. Surface gravity becomes immense. Escape velocity rises dramatically. A dropped object, assuming any such experiment could be sensibly attempted, would stop being a casual example very quickly. The collapse that creates such density is not merely shrinking, it is transformation. A cotton ball compressed into a pebble is still cotton. A stellar core compressed into a neutron star is not still normal star stuff. Its internal state has changed profoundly. Now, what about spin? Before collapse, the original star likely rotated at some rate, perhaps modestly by neutron star standards. As the core contracts dramatically, conservation of angular momentum comes into play. Just as a skater spins faster by pulling arms inward, a shrinking stellar core can rotate much faster after collapse. A large, slowly rotating object becomes a tiny, rapidly rotating one. So even before later recycling by a companion star, collapse itself can produce a swift spinner. This matters for PSR J1748-2446 AD, because its later extreme speed likely builds on foundations laid here. Collapse creates the compact remnant. Compactness permits fast rotation. Later accretion may sharpen that speed into the record-setting rate we observe. Extreme present states often require multiple earlier steps. The collapse is one of them. There is another hidden gift in supernovae worth mentioning. The material blasted outward enriches space with heavy elements forged in stellar interiors and during the explosion itself. Calcium, oxygen, silicon, iron, and many other ingredients of planets and bodies are spread into future clouds. The atoms in bones, rocks, tools, and blood have ancestral ties to dead stars. So while one star ends, future systems gain raw material. Destruction and generosity arrive together. This is common enough in cosmic history that our own existence depends on it. The death of earlier stars made Earth chemically possible. That can soften the harshness of collapse. It is not only ending, it is distribution. Still, for the star itself, the moment everything changes is mercilessly direct. There is no committee meeting, no extension request, no pause while it reflects on lessons learned. Physics proceeds. Once support fails, gravity acts. This can feel severe when described plainly, yet there is also honesty in it. Stars live by balances. When balances end, new states follow. The same laws that allowed a star to shine eventually determine how it falls. Nothing personal, nothing wasted, just process. If an observer could watch from a safe and impossible vantage point, the sequence might seem surreal. A familiar star brightens in its final phases. Collapse begins invisibly inside. Then an explosion tears through surrounding layers. Afterward, where once there was a star, there remains a compact remnant perhaps no wider than a city, spinning rapidly and cooling into a new identity. From distance, a point of light changes category. From within physics, everything changed. The newborn neutron star would also possess a strong magnetic field, inherited and intensified by collapse. Magnetic flux conservation means fields can become dramatically stronger as size decreases. What was once stellar magnetism becomes something far more intense, concentrated into a smaller body. Spin plus magnetism help create pulsar behavior. So collapse does not merely make a dense object. It assembles ingredients for later lighthouse-like pulses. Again, multiple consequences arrive at once. Smaller size, greater density, faster spin, stronger magnetic effects, new observational signatures. A star that once shone by fusion may later announce itself by rhythm. That is an extraordinary change of personality. There is a psychological comfort, strangely enough, in learning that the universe itself contains moments of sudden transition. Human lives often include long, steady phases followed by abrupt changes, moves, losses, beginnings, illnesses, recoveries, decisions, surprises. We sometimes assume change should be gradual because gradual feels fair. Nature disagrees. Sometimes change is gradual, sometimes it waits, then it happens quickly. Stars know this too. Of course, not every collapse creates the same remnant. Some cores exceed the mass limits that neutron degeneracy and nuclear forces can support. Those may continue inward toward black holes. Others may produce different neutron star masses, magnetic properties, or spin histories. Real astrophysics is varied and detailed. But for our story, the key fact is simple. PSR J1748-2446 AD could not exist without collapse. Without the catastrophic ending of a massive earlier star, there would be no tiny ultra-dense object available to spin hundreds of times each second. The fastest known spinner is built on a prior star's failure to remain what it was. That may sound grim. It is not. It is transformative. Many of the universe's most interesting things are second forms. White dwarfs are stellar afterlives. Neutron stars are compressed continuations. Black holes are further consequences. Even planets like Earth are assembled from leftovers of earlier stars. First versions matter, later versions can astonish. Picture for a moment the most solid thing you can easily imagine. Perhaps a block of steel, a granite mountain, a vault door in a film that seems designed mainly to reassure viewers that nothing could possibly get through it. We associate heaviness and hardness with strength, permanence, resistance. Dense things feel dependable. They stay where they are placed. They require effort to move. They seem substantial in a world where many things are not. Then astronomy enters the room, sits down politely, and changes the scale. Because compared with the matter inside a neutron star like PSR J1748-2446 AD, steel is spacious. Granite is airy. Even the densest ordinary materials around us are, in a certain sense, mostly emptiness arranged with confidence. That statement sounds dramatic, but it begins with atoms. Everyday matter is made of atoms. At the centre of each atom is a tiny nucleus containing protons and neutrons. Around it is a cloud of electrons. If the nucleus were the size of a pea in the middle of a stadium, much of the atom would be open space by volume. Matter feels solid not because atoms are packed wall-to-wall like bricks, but because electromagnetic forces prevent them from passing through one another easily. Your hand rests on a table, not because the hand and table are touching in the intuitive sense, but because the charged particles in each strongly object to sharing the same location. Polite refusal creates furniture. That is normal matter. Neutron star matter is what happens when gravity becomes so intense that normal arrangements no longer survive. When the massive parent star of PSR J1748-2446 AD collapsed, the pressure in its core rose beyond anything found in ordinary environments. Electrons were forced into protons. The separate architecture of atoms broke down. Matter was compressed until the distinctions that define everyday solids ceased to function in familiar ways. Empty space inside atoms was largely squeezed out. What remained became dominated by neutrons packed together under immense pressure, along with more complicated layers and particles depending on depth and exact conditions. This is why the name neutron star exists. It is not merely a star made of the same old stuff in a smaller package. It is matter reorganized under violence. If that sounds unsettling, it can also be beautiful. The universe keeps revealing new states of reality when conditions change enough. Water can be ice, liquid, steam. Carbon can be graphite or diamond. Matter can be atoms in a chair. Matter can be nuclear density material in a spinning stellar remnant. Same universe, different pressure. Now let us attempt the famous comparison. You may have heard that a teaspoon of neutron star material would weigh billions of tons on Earth. Versions of the number vary depending on assumptions, but the spirit of the statement is correct. A tiny sample would have absurd mass by everyday standards. A spoonful, enough weight to embarrass infrastructure, enough density to make scales resign. Of course, there is no practical way to scoop a teaspoon from a neutron star and bring it home. The sample would not politely remain a teaspoon under Earth conditions, and the process would involve difficulties not covered by standard kitchen safety guidance. Still, the analogy helps. Small volume, vast mass, that is the essence. To understand why, imagine compressing the mass of the Sun into a sphere perhaps 20 kilometers across. The Sun is over 1 million times the volume of Earth, yet a neutron star packs stellar mass into something the size of a city. This is not tidying up. This is compression on a level that makes ordinary language wobble. A useful mental image is to compare a sponge with a metal ball. But even that fails because a sponge still contains structure recognizable to us. Neutron star matter exists in a regime where the rules are governed by quantum mechanics, nuclear forces, relativity, and crushing gravity. It is not simply squeezed matter, it is transformed matter. Let us move layer by layer, gently. The outermost surface of a neutron star is thought to contain a crust. Even this crust would be unlike anything on Earth. Nuclei arranged in dense lattices, electrons moving freely, pressures rising rapidly with depth. Descend further, and the nuclei become more neutron-rich. Eventually strange pasta-like phases may appear. Yes, pasta. Scientists use terms like lasagna, spaghetti, and gnocchi for theoretical nuclear structures in the crust, because when nuclei are deformed under immense pressure, they may arrange into sheets, rods, and blobs. This is not because the universe is hungry, though the naming suggests morale was good that day in the physics department. These nuclear pasta phases arise because competing forces, attraction and repulsion at tiny scales, can create organized shapes. Even under crushing pressure, matter still finds geometry. Go deeper still, and separate nuclei may dissolve into a dense fluid, dominated by neutrons with some protons, electrons, and perhaps other particles mixed in depending on conditions. At the core, uncertainty increases. This is one of the great open questions in astrophysics. The densities may be so extreme that exotic states appear, hyperons, condensates, deconfined quark matter, or other possibilities still under study. In plain language, we're not entirely sure what the deepest interior of a neutron star is made of, and that is wonderful. It means reality still contains locked rooms. PSR J1748-2446 AD is not just an object we understand. It is also an object that continues to challenge us. Now consider gravity at the surface. If you stood on a neutron star, which again you must not attempt, gravity would be immensely stronger than on Earth. Dropping an object would become a very brief story. A human body would not experience the event positively. Light itself would lose energy climbing away, producing measurable gravitational redshift. Even time would behave differently in such strong gravity. We will visit that later, but it is worth mentioning now because dense matter and gravity are partners in this story. The matter is crushed because gravity is powerful. Gravity is powerful because so much mass is packed into so little space. Cause and consequence become neighbours. There is another subtle point worth enjoying tonight. When people hear dense, they often think hard. But hardness is an everyday material property describing resistance to scratching or deformation under certain conditions. Neutron star matter is not hard in the furniture sense. It is something more fundamental and stranger. It is matter held in a balance of forces at enormous density. Trying to compare it to steel is like comparing a thunderstorm to a faucet because both involve water. The categories only overlap so far. And yet, despite all this extremity, neutron stars are real measurable objects. We detect them. We time their pulses. We estimate masses and radii. We model interiors. We observe collisions of neutron stars through gravitational waves and electromagnetic signals. The bizarre is not merely theoretical decoration. It is out there. That can be calming in a curious way. The universe is larger than intuition, but not inaccessible to reason. We may not be able to touch neutron star matter, but we can learn about it. We can infer properties through observation, mathematics, and patience. Humanity has an odd and admirable habit of understanding places it cannot visit. Now, let us bring this back to PSR J1748-2446 AD specifically. Why does crushing matter matter for spinning? Because compactness allows speed. If you shrink a massive object dramatically, its moment of inertia changes. Rotation can accelerate. A giant diffuse star cannot spin hundreds of times each second and remain itself. A compact neutron star can approach such rates because its mass is concentrated near the centre. Small radius changes everything. This is why stellar collapse was essential. Without crushing the parent star's core into neutron star form, there would be no platform for the extraordinary spin we now observe. The fastest known spinner depends on the most compressed ordinary remnant nature commonly allows before black hole territory begins. That alone is an elegant sentence in the language of physics. There is also a poetic contrast we should phrase plainly rather than poetically. The star became smaller and denser, yet more dramatic. We often equate size with importance. Bigger house, bigger machine, bigger noise, bigger presence. But neutron stars reverse that instinct. Something tiny by stellar standards can become vastly more extreme than the giant star that preceded it. Compression creates significance. That can apply outside astronomy too. Concentrated effort, focused thought, distilled skill, compact truths. Size is not the only path to power. Still, we must not romanticize the process. The route to neutron star matter was catastrophic collapse. The universe is under no obligation to be gentle when making remarkable things. Now imagine if one could hold a pebble-sized fragment of neutron star matter, stabilized somehow by impossible technology. It would contain staggering mass. Its gravity would be noticeable. Its internal pressure story would be beyond engineering. Fortunately, this remains imagination rather than shipping logistics. Even transporting the concept feels difficult. Yet these comparisons serve a purpose. They help our minds approach scales otherwise too remote to feel. A city-sized star, a spoonful heavier than mountains, atoms dismantled, matter arranged into phases named after pasta, a surface where gravity becomes severe and time itself is affected. All of that belongs to the same category of object quietly spinning in space. There is humility in that realization. Our daily world trains us on one narrow slice of possible matter behavior. We then assume normal is universal. It is not. Normal is local. Elsewhere, matter behaves according to the same laws under different conditions and reveals possibilities hidden from everyday life. The table beside you teaches one lesson of physics. PSR J1748-2446 AD teaches another. Both are true. Both are valuable. One supports your cup. One tests nuclear theory. And somewhere between those two truths sits the full richness of reality. Scientists often speak of the equation of state for neutron star matter. This means the relationship between pressure, density, temperature, and internal composition. Different theories predict different radii and behaviors for stars of certain masses. By observing neutron stars carefully, especially extreme ones, we can narrow those possibilities. So PSR J1748-2446 AD is not only astonishing because it spins fast, it may also help constrain what crushed matter can withstand. If it rotates stably at such speed, certain internal models become more plausible than others. A record becomes data. Wonder becomes measurement. That transformation is one of science's finest habits. If this object is so dense and so compact, how did it become such a rapid spinner in the first place? Watch a figure skater for long enough and you will witness one of physics' favourite demonstrations. They begin with arms extended, body open, rotation controlled and moderate. Then the arms draw inward. The body becomes more compact. Suddenly the spin quickens. What looked graceful becomes astonishing. No hidden motor appears. No secret boost is applied. The change comes from geometry and a deep conservation law woven through the universe. The same principle helps explain why PSR J1748-2446 AD spins so fast. A star, it turns out, can perform the cosmic version of the ice skater effect. Long before it became a neutron star rotating hundreds of times each second, this object was much larger. Its ancestor was an ordinary star in the sense that it was a normal stellar body supported by fusion, with a radius vastly larger than the compact remnant that exists now. Large things do not need to spin quickly to contain significant rotational motion. Small things often do. When the original star reached the end of its life and its core collapsed, that core shrank dramatically. What had once occupied an enormous region was compressed into something perhaps 20 kilometers across. The radius decreased by a staggering amount, and when rotating matter shrinks inward, spin rate tends to rise. This happens because of conservation of angular momentum. That phrase sounds formal, but the idea is friendly. The universe is rather stubborn about certain quantities. Energy, momentum, electric charge, and angular momentum are among the values nature tracks carefully. Angular momentum is the rotational cousin of ordinary momentum. If something is spinning and no strong external torque interferes, the total rotational budget is conserved. So if an object becomes smaller while keeping much of that budget, it must spin faster. The skater pulls arms inward. The office chair rotates faster when you tuck in your legs. A diver curls mid-air. A collapsing stellar core becomes a rapidly rotating neutron star. Same principle, different consequences. This is one of the joys of physics. The rules that govern a child spinning on a playground can also govern the birth of exotic stars. Scale changes wildly. Law remains consistent. Now, let us slow down and picture it. Imagine a large merry-go-round turning steadily. Most of its mass lies far from the centre. That matters because mass farther from the axis contributes strongly to rotational inertia, the tendency to resist changes in spin rate. Now imagine magically drawing all that mass much closer to the centre while preserving angular momentum. The merry-go-round would speed up. A lot. In stars, collapse does something similar. The original stellar core might rotate once every hours, days, or some other moderate interval depending on its history. Then gravity compresses that core into a neutron star. Radius plunges. Moment of inertia drops dramatically. Rotation rate rises. A leisurely stellar turn can become a furious compact spin. So even before any later complications, the collapse itself gives us a fast object. But PSR J1748-2446 AD is not merely fast, it is exceptionally fast. That means collapse alone may not tell the whole story. To understand the full speed, we need to add another ingredient later in the star's life: companionship. Many millisecond pulsars are thought to be recycled neutron stars in binary systems. A companion star transfers matter onto the neutron star over long periods. That infalling matter carries angular momentum. As it spirals inward through an accretion disk, it effectively spins the neutron star up further, like steadily pushing a carousel in exactly the helpful direction. So there are two major acts in the spin story. First, collapse shrinks the star and accelerates rotation. Later, accretion from a companion can push it to extreme rates. PSR J1748-2446 AD likely benefited from both. The result is a compact remnant rotating around 716 times each second. This makes the object less like a random cosmic oddity, and more like the outcome of understandable processes applied patiently over time. That is often how extraordinary things happen in nature. Not magic. Accumulated consequence. There is something pleasing about that. We sometimes imagine records as sudden miracles, a leap, a flash, a one-time impossibility. But many records come from gradual refinement, training, iteration, favourable conditions, persistence. Even stars apparently can be coached upward through long-term support. Now let us return to the skater one more time, because the analogy has limits worth noticing. A human skater changes shape voluntarily using muscles. A star does not decide to pull in its arms. Gravity does the choreography. The collapsing core cannot negotiate. Once internal support fails, contraction proceeds under physical law. Nature performs the motion automatically, and unlike the skater, the star's change is extreme beyond human experience. A body once thousands or millions of kilometers across leaves behind a remnant measured in tens of kilometers. That is not posture adjustment. That is transformation. Still, the core lesson survives. Compactness favors speed. You can see hints of this elsewhere. Earth rotates once every 24 hours. Jupiter, larger but with different internal history and structure, rotates in about 10 hours. White dwarfs, the remnants of lower mass stars, can spin more quickly than their parent stars. Neutron stars, smaller still and denser by far, can rotate with breathtaking rates. Compression and rotation often travel together. Now, there is a sensible question waiting in the room. If shrinking increases spin so much, why do stars not all become absurdly fast rotators automatically? Because real astrophysics is complicated. Stars lose angular momentum through winds and magnetic interactions during life. Explosions can eject material. Collapse may not preserve every detail neatly. Internal layers can rotate differently. Binary interactions may help or hinder. Some remnants are born spinning quickly, others more slowly. Nature obeys laws but not cartoons. That is why extreme objects like PSR J1748-2446 AD are special. They represent particular histories where many factors aligned. Another useful thought experiment: imagine holding a pizza dough disc. Spin it slowly while it is wide and floppy. Then imagine shrinking it while preserving rotational character. The spin would rise. The analogy is imperfect and slightly disrespectful to neutron stars, but it captures the geometry. Radius matters immensely. In formulas, angular momentum depends on moment of inertia and angular velocity. Moment of inertia depends strongly on how mass is distributed relative to the axis. Pull mass inward and less inertia remains. Angular velocity rises if angular momentum is conserved. You need not memorize equations to feel the principle. Closer in means faster around. There is also something emotionally calming about conservation laws. In a world that often feels chaotic, physics contains deep bookkeeping. Quantities are tracked, changes are constrained, outcomes follow structure. The universe is creative but not careless. PSR J1748-2446 AD spins rapidly because its history plus the laws of motion allow it, not because reality occasionally throws dice without rules. Now think about time. Every second you experience contains hundreds of rotations of this star. Yet those rotations are not frantic in the star's own sense. It is not hurrying. It is simply in equilibrium with its circumstances. Humans often confuse speed with stress because our speed usually comes bundled with deadlines, alarms, traffic, and regrettable multitasking. Cosmic speed can be serene. A pulsar rotating hundreds of times each second may be calmer, in a physical sense, than a commuter trying to merge lanes. That is a useful perspective. There is another subtlety. When a neutron star spins quickly, its shape may deviate slightly from a perfect sphere. Rotation can cause equatorial bulging, just as Earth bulges modestly at the equator due to its spin. For a millisecond pulsar, such effects can matter scientifically. So fast rotation is not merely a number. It changes structure, stability, magnetic behavior, and observational signatures. Speed shapes identity, and identity shapes what astronomers can learn. When researchers observe objects like PSR J1748-2446 AD, they are not just impressed. They are extracting information about matter, gravity, stellar evolution, and rotational limits. The star's spin is both spectacle and evidence. That dual role is common in science. A rainbow is beautiful in optical physics. A thunderstorm is dramatic in atmospheric dynamics. A pulsar is astonishing and data-rich. Now perhaps the most charming part of this whole story is that one of the fastest known stellar spinners can be explained partly by the same concept demonstrated in skating rinks and swivel chairs. Sometimes the universe meets us halfway. It gives us gigantic mysteries attached to familiar principles. That generosity allows understanding. Far from Earth, in regions where no ocean exists and no shoreline waits, the universe still found a way to build lighthouses. Not towers of stone, not beams sweeping across fog, not lonely keepers polishing glass while writing thoughtful journals. Instead, it built pulsars. PSR J1748-2446 AD belongs to this remarkable family of objects. It is not only a neutron star spinning at extraordinary speed, it is also a pulsar, which means it sends out beams of radiation that sweep through space as the star rotates. When one of those beams crosses Earth's line of sight, our instruments detect a pulse. That repeated signal is how many pulsars first introduce themselves. Pulse, pulse, pulse. Sometimes slow enough to count, sometimes so fast that the pulses blur into astonishing precision. This is why pulsars are often compared to lighthouses. A lighthouse does not blink because the lamp turns on and off. It shines continuously while the beam rotates. To an observer standing in the right place, the light appears in intervals as the beam passes by. The pulsar behaves similarly. The star rotates. The beam sweeps. We receive flashes only when geometry favours us. That distinction matters because the pulsar is not truly switching itself on and off each time. It is rotating steadily while directing radiation into narrow regions of space. In that sense, a pulsar's rhythm is partly about the star and partly about where we happen to be. The universe often reminds us that perspective matters. Now, before we go further, let us ask a reasonable question. Why does a neutron star emit beams at all? The answer begins with magnetism. Neutron stars often possess immensely strong magnetic fields. During stellar collapse, magnetic fields from the original star can become concentrated and intensified as the core shrinks. Imagine taking magnetic lines spread through a huge region and compressing them into something city-sized. The result can be extraordinary field strengths. Then add rapid rotation. A spinning magnetized object can accelerate charged particles around it. Those particles race along magnetic field lines, emitting radiation across different wavelengths depending on the system. Radio waves are especially famous in pulsar astronomy, though pulsars can also emit X-rays, gamma rays, and more. The magnetic poles, importantly, are not always aligned with the rotation axis. That mismatch creates the lighthouse effect. If the magnetic axis were perfectly aligned with the spin axis, the geometry would be simpler and often less dramatic observationally. But tilt the beam, spin the star, and the beam sweeps circles through space. If Earth lies in one of those circles, we notice. If not, the pulsar may remain hidden from us. That means the galaxy likely contains many pulsars we do not detect simply because their beams never cross our line of sight. Reality does not require visibility to exist. That is true of stars, feelings, and many household crumbs under furniture. Pulsars were first discovered in 1967 by Jocelyn Bell Burnell and Anthony Hewish through radio observations. The signals were so regular that they briefly inspired jokes about extraterrestrial intelligence. One early nickname was LGM, for Little Green Men. This says something charming about science. Faced with a baffling, precise signal from the sky, researchers investigated seriously while still retaining humour. Soon the real explanation emerged: rapidly rotating neutron stars. Since then, pulsars have become one of astronomy's richest classes of objects. Some rotate once every few seconds, some every fraction of a second. Millisecond pulsars, like PSR J1748-2446 AD, rotate hundreds of times each second. Each pulse is like a tick from an extreme clock, and clocks, as humans know well, are useful. What makes pulsars especially valuable is their regularity. Many pulse with astonishing consistency. Their timing can be predicted so precisely that deviations reveal other phenomena: orbital companions, gravitational effects, motion through space, interstellar gas, and even the possibility of detecting gravitational waves through networks of pulsars timed across the galaxy. Imagine using distant collapsed stars as measurement tools. It sounds theatrical. It is standard astrophysics. PSR J1748-2446 AD, because of its rapid spin, belongs to the elite category of millisecond pulsars. These are often old neutron stars that have been spun up through accretion from companion stars. We will return to that relationship again because it is one of the most elegant partnerships in stellar evolution. For now, the key point is this: some pulsars are born fast, others are made faster later. Either way, once they become pulsars, they become beacons. Now let us think about darkness. Space is often described as empty, black, silent. There is truth in that description, but only partly. Space is also full of signals, fields, particles, radiation and motion. Much of it lies outside human senses. We do not naturally hear radio waves or see X-rays. So a pulsar's lighthouse beam is not usually visible to naked eyes as a sweeping cinematic spotlight. It is often detectable through instruments tuned to the right wavelengths. This is another recurring lesson of science. Reality is richer than our senses. Our eyes show one version of the universe. Telescopes reveal many others. A radio telescope listening to a pulsar hears order where naked sight sees darkness. There is something comforting about that. Hidden patterns can exist even when not immediately obvious. Now imagine standing, impossibly and safely, near PSR J1748-2446 AD. The star spins around 716 times each second. Its magnetic environment would be severe, radiation intense, gravity extreme. As it rotates, beams would sweep outward with relentless speed. You would not be lingering for photographs, but from far away, on Earth, we can receive those signals as data. A gentle pulse in a telescope's output can represent one of the most violent classes of objects in nature, behaving with exquisite regularity. The contrast is lovely. Extreme cause, elegant effect. There is another subtle point about pulsar pulses. They are not all identical little clicks. Pulse profiles can be complex. Shapes depend on geometry, emission regions, frequency, magnetic structure, and observational details. Some pulsars have multiple peaks, some glitch, some drift, some switch states. Nature rarely stops at the simplest version of an idea, yet even with complexities, the basic lighthouse analogy remains wonderfully useful. Rotating beam, periodic sweep. Observer receives intervals. This periodicity allows astronomers to determine spin rates with great precision. If you measure the arrival times of pulses carefully, you can infer rotation, slow changes in spin, orbital motion if the pulsar has a companion, and other subtle effects. It is rather like listening to a drummer so steady that tiny timing shifts reveal movement in the stage beneath them. Pulsars also help to confirm aspects of general relativity. The famous Hulse-Taylor binary pulsar showed orbital decay consistent with energy loss through gravitational waves long before direct detections by LIGO. Once again, collapsed stars became tools for testing deep physics. A lighthouse, apparently, can also be a laboratory. Now let us return emotionally to the image itself. There is something naturally soothing about repeated distant signals. Humans like rhythm. We sleep to rain, fans, waves, trains, breathing, and soft repetition. Predictable intervals calm the nervous system. Perhaps that is why pulsars capture imagination so easily. They turn cosmic violence into steady cadence. A star exploded long ago. Its core collapsed. Magnetic fields intensified. Matter was crushed beyond intuition. And now, ages later, it sends regular pulses through space. From chaos came tempo. This pattern appears often in nature. Forests regrow after fire. Bodies heal after injury. Weather settles after storms. Remnants sometimes become more orderly than origins. PSR J1748-2446 AD is a striking example. Whatever dramatic events formed and accelerated it, what reaches us now is rhythm. Of course, not all neutron stars are pulsars forever. Over time, many slow down. Their beams may weaken or no longer sweep past Earth. Some become harder to detect. The lighthouse can fade from our perspective even while the star remains. That too feels familiar. Signals can stop not because something has vanished, but because alignment changed. Now, because tonight's subject is the fastest known spinner among confirmed pulsars, its pulses arrive with extraordinary rapidity. Hundreds each second. That means the beam sweeps past us again and again in intervals shorter than conscious counting. No human lighthouse keeper could match such dedication. No ordinary machine could do so under stellar conditions, yet a compact remnant in a globular cluster does exactly that. This should also remind us that names like dead star can be misleading. Neutron stars are often described as stellar remnants, which is true in one sense. Fusion life is over. The original star is gone. But these remnants are hardly inactive. They rotate, radiate, interact with companions, bend space-time, generate fields, and teach physics. Some endings remain busy. There's also a quiet philosophical comfort here. We often fear darkness as emptiness, but cosmic darkness is full of hidden structure. Beams sweep through it, signals cross it, ancient clocks tick within it. The black background of space is not blankness but contrast. Without darkness, the lighthouse means less. Without silence, rhythm is harder to hear. Without distance, wonder shrinks. So when astronomers detect pulses from a source like PSR J1748-2446 AD, they are not merely collecting numbers. They are receiving evidence that order persists across vast emptiness. A rotating object smaller than a city can announce itself across thousands of light years. That is a powerful sentence. Somewhere in the Milky Way, a compact star turns hundreds of times each second and sends signals into the dark. We detect those signals with instruments, we graph them, we measure them, we use them to test physics, and then, because humans are wonderfully incapable of resisting curiosity, we ask another question. If these stars produce pulses, what would one actually sound like if translated for human ears? What does it sound like? Now, a careful answer comes first. Space, in the ordinary sense, is not carrying sound the way air in a room does. Sound is a vibration travelling through a medium such as air, water, or solid material. Space between stars is far too thin for sound waves to travel in the familiar way. If you floated beside PSR J1748-2446 AD, ignoring the many reasons you should not be there, you would not hear a dramatic mechanical buzzing through your ears. No thunderous roar, no giant spinning whistle, no cosmic dentist drill, thankfully. So when we speak of the sound of a pulsar, we mean something more subtle and, in some ways, more beautiful. We take signals the star emits, often radio pulses, and translate timing or frequency data into audible sound. We convert patterns into something human senses can appreciate directly. In short, we let the star borrow our hearing. That is one of science's loveliest habits. When nature speaks in wavelengths we cannot sense, we build tools and interpreters. Infrared becomes image. Radio becomes map. Timing becomes rhythm. A pulsar becomes music of a kind. PSR J1748-2446 AD rotates around 716 times each second. That corresponds to a frequency of roughly 716 Hz if one pulse is associated with each rotation. Human hearing generally spans from about 20 Hz to 20,000 Hz, varying with age and circumstance. That means the spin rate sits comfortably within the audible range. If rendered directly as a tone, it would be a steady pitch, not impossibly low, not painfully high, somewhere in the territory of a clear electronic hum. Think less explosion, more precision, less chaos, more sustained signal. This surprises many people. We often imagine exotic astronomy should sound grand and cinematic. Deep booms, metallic drones, choirs of dramatic concern. But a rapidly spinning pulsar can translate into something cleaner, almost modest. A tone, a buzz, a persistent note. There is something delightful in that mismatch. A star with immense gravity and matter crushed beyond imagination may sound, when converted, more like an obedient instrument than a monster. Of course, the exact result depends on how scientists choose to sonify the data. There is no single official soundtrack. One can map pulse timing into clicks, into pitched tones, into percussive patterns, into layered soundscapes, or into accelerated and slowed versions that emphasize structure. The data allows interpretation. Humans supply artistry. Suppose we choose clicks. Then PSR J1748-2446 AD would produce a stream so rapid that individual clicks blur into texture. At slower pulses you can hear tick, 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 like a patient metronome. At hundreds of pulses per second, those ticks merge into a continuous tone shaped by subtle modulation. The rhythm becomes pitch. That transformation is deeply important in acoustics. When repetition becomes fast enough, separate beats fuse into musical note. Strike a table once each second and you hear taps. Vibrate a string hundreds of times each second and you hear tone. So a fast pulsar crosses the border between percussion and melody. That feels oddly poetic, though we shall keep our feet on the ground and call it acoustically interesting. Now imagine another version. Take the actual pulses and slow them down enormously. Stretch time so humans can perceive the spacing. Suddenly the impossible spinner becomes a sequence of beats again. Tap, tap, tap. Only now each tap represents a rotation that originally happened in milliseconds. This is another trick science performs beautifully. It changes scale so our senses can participate. We do this visually too. We speed up flower growth. We slow down hummingbird wings. We map invisible radiation into colours. We enlarge cells. We compress geologic time into diagrams. Understanding often requires translation. The universe is not obligated to be human-sized. We meet it halfway. There is something calming about pulse sounds in particular. Repetition tends to soothe the mind when it is regular and non-threatening. Fans, rain, distant trains, clocks, breathing, ocean waves. Our nervous systems often respond well to patterned continuity. Pulsars offer precisely that, continuity. A collapsed star keeps time across years, decades, longer. Signals repeat with extraordinary consistency. In some cases, pulsars rival clocks in stability over certain timescales. So if you listen to a pulsar rendering, you're hearing not just a sound design choice, but evidence of remarkable order. That can be surprisingly moving. Long before humans existed, stars lived and died. Some left behind neutron star remnants. Those remnants spun in darkness. Ages later, a species on one small planet built radio telescopes, gathered faint signals, converted them to sound and listened. It is difficult not to admire that sequence. Now let us return specifically to PSR J1748-2446 AD. Because it spins so quickly, any direct audible rendering tied to spin frequency would be a relatively high steady tone. But real pulsar signals are richer than one pure frequency. Pulse shapes are not perfect mathematical spikes. Interstellar space disperses radio waves. Magnetic geometry matters. Instrument bandwidth matters. Processing choices matter. The result can include texture, wobble, harmonics, modulation. So the voice of a pulsar may feel less like one clean beep and more like a characterful machine with subtle grain. And yes, astronomy occasionally gives stars personalities through data. There is also the role of distance. Signals from pulsars travel through interstellar medium, thin gas, plasma, magnetic environments. Lower radio frequencies can be delayed relative to higher ones. This dispersion can smear pulses until corrected mathematically. When scientists remove those propagation effects, they recover cleaner timing. In a sense, the galaxy edits the sound on the way to us. That is charmingly inconvenient. Even empty space likes to add texture. You might wonder whether pulsars are unique in this sonic appeal. Not entirely. Many astronomical phenomena are translated into sound. Black hole accretion variations, solar oscillations, plasma waves from planets, seismic data from Mars, cosmic microwave background analyses. But pulsars are especially satisfying because they already possess rhythm. Humans love rhythm. We march to it, dance to it, calm infants with it, organise music through it, and occasionally clap incorrectly during songs with great confidence. A pulsar gives rhythm freely. No rehearsal needed. There is another angle worth noticing tonight. We often think sight is the dominant sense of science. Telescopes, images, photographs, maps. Yet hearing can reveal patterns quickly. The brain is excellent at noticing changes in tempo, pitch, irregularity, and repetition. Sonification is not merely decorative, it can be informative. A sudden glitch in pulsar timing, a drift in pulse spacing, a modulation pattern. These may become obvious to the ear in ways graphs sometimes hide. So when we listen to stars, we're not abandoning rigour. We are adding another route to perception. Science is practical enough to use whichever sense helps. Now let us imagine gently a nighttime room much like yours. Dim light, quiet air, a listener half awake, half drifting. In headphones, a translated pulsar signal hums steadily. That sound began as radiation from a neutron star thousands of light years away. Its source is smaller than a city, its gravity is immense, its matter is exotic, its spin outrageous, and yet what reaches you is simple repetition. There is something almost tender in that compression of complexity into calm rhythm. We experience this often in life. A watch tick hides engineering. Rain hides atmospheric dynamics. Heartbeat hides biology. Pulsar tone hides catastrophic stellar history and dense matter physics. Surface simplicity can conceal magnificent depth. Of course, not everyone finds electronic hums relaxing. Some may prefer rain, wind, or silence. Perfectly fair. The point is not that pulsars are nature's best sleep machine, though one could imagine a niche market. The point is that the universe contains patterns that can be translated into intimacy. Data becomes sound. Distance becomes presence. Abstraction becomes experience. And once that happens, astronomy changes character. It is no longer only about remote objects. It becomes relationship. We hear the cosmos not because it literally sings in air, but because we learned how to listen differently. That lesson extends beyond stars. Many truths are inaudible until translated. Many patterns are invisible until mapped. Many meanings are hidden until reframed. In the story of PSR J1748-2446 AD, there are really two discoveries worth appreciating. The first is the star itself. The second is that humans noticed it at all. That may sound obvious, but it deserves respect. This is not a bright object visible to the naked eye. It is not a dramatic streak across the sky or a nearby beacon politely announcing its presence. It is a tiny neutron star, thousands of light years away, hidden inside a crowded region packed with stars sending rapid radio signals that must be separated from noise, measured carefully and interpreted correctly. In other words, the universe did not make this easy. And perhaps that makes the discovery better. We sometimes imagine astronomy as people looking through telescopes and immediately gasping at glorious wonders. Occasionally that happens. More often, modern discovery is patient work. Receivers hum. Computers process streams of data. Signals are searched for patterns. False alarms are rejected. Timing is checked. Statistics are argued over with admirable seriousness. Then, after enough careful effort, something real emerges. PSR J1748-2446 AD was announced in 2004 as an extraordinarily rapid pulsar, discovered through radio observations. Its measured spin frequency of around 716 times per second made it the fastest spinning known neutron star at the time, and it has remained one of the great record holders of pulsar astronomy ever since. No fireworks marked the moment in the sky. No celestial certificate descended, just data, discipline, and the quiet thrill of realizing nature had once again exceeded expectation. To understand how such an object is found, let us begin with radio telescopes. Unlike optical telescopes, which gather visible light, radio telescopes detect radio waves. These waves are part of the electromagnetic spectrum, just like visible light, X-rays, infrared, and microwaves, but with longer wavelengths. Many astronomical objects emit radio signals, including galaxies, gas clouds, planets, and pulsars. Pulsars are especially suitable for radio discovery because their beams can sweep past Earth as repeating bursts. If your telescope is pointed in the right direction, and if the pulsar's beam intersects our line of sight, you may detect a periodic signal. That sounds straightforward. It is not. Real observations contain noise from instruments, Earth's environment, human technology, cosmic sources, and the sheer complexity of weak signals travelling across the galaxy. A pulsar search involves combing through vast amounts of data, looking for repeating patterns hidden inside clutter. Imagine standing in a crowded room where thousands of people are talking, machinery is humming, dishes are clattering, and somewhere across the hall someone taps a spoon on a glass at perfectly regular intervals, hundreds of times each second. Now, imagine trying to identify not only that the tapping exists, but exactly how fast it repeats. That is closer to the challenge. Astronomers use signal processing techniques to search for periodicity. They transform data mathematically, test candidate frequencies, correct for known distortions, and verify that a pattern is genuine rather than accidental or terrestrial interference. Pulsars reward persistence. Now add another complication. PSR J1748-2446 AD spins extremely fast. Very fast pulsars can be harder to detect because their pulses come so close together. If the signal is weak, smeared by interstellar effects, or affected by orbital motion in a binary system, detection becomes more difficult. And yet, there it was, a tiny compact star announcing itself through precision. There is something deeply satisfying about this. The star had been spinning long before humans existed. It was sending pulses long before radio technology was invented. The signal crossed space for ages unnoticed. Then one species on one planet developed enough mathematics, electronics, and stubborn curiosity to hear it. The universe was already speaking. We became capable of listening. That phrase applies to much of science. Now let us discuss where this remarkable object lives, because location matters in astrophysics. PSR J1748-2446 AD resides in a globular cluster called Terzan 5. Globular clusters are among the oldest and most beautiful structures associated with galaxies. They are dense, spherical swarms of stars bound together by gravity, often containing hundreds of thousands, sometimes millions of stars in relatively compact volumes. If our local stellar neighbourhood is like a quiet suburb with generous spacing, a globular cluster is more like a packed ancient city centre, where everyone lives much closer than seems comfortable. The night sky from within such a cluster would likely be extraordinary. Stars would appear far more numerous and brighter than what we know from Earth's relatively spacious region of the Milky Way. It would also be a poor place to expect privacy. Terzan 5 lies toward the central region of our galaxy, and is particularly interesting. For many years it has been known as a rich environment for unusual stellar systems, including multiple pulsars. Dense clusters like this are natural factories for exotic objects, because close encounters between stars happen more often. In wide open space, stars usually keep to themselves. In crowded clusters, relationships become complicated. Gravity encourages introductions. Binary systems can form, be disrupted, exchange partners, tighten, widen, or evolve through close passages. Compact remnants like neutron stars can acquire companions. Matter can transfer from one star to another. Rotational histories can be rewritten. This is exactly the sort of environment where millisecond pulsars are expected to thrive. That matters for PSR J1748-2446 AD, because extremely fast pulsars are often recycled. A neutron star born from stellar collapse later gains matter from a companion star. As material spirals inward, it carries angular momentum and gradually spins the neutron star faster and faster. So Terzan 5 is not merely an address, it is part of the explanation. Place shapes possibility. A quiet, isolated region may produce one history. A dense stellar cluster may produce another. That is true for stars and in gentler ways for people. Now picture the cluster itself. Globular clusters are roughly spherical because gravity has had immense time to smooth their overall distributions. Many are ancient, dating back to the early history of the Milky Way. Their stars are often old and relatively metal-poor compared with younger populations, though Terzan 5 is particularly complex and has shown evidence of multiple stellar populations and unusual chemical history. That has made it scientifically fascinating beyond just pulsars. Terzan 5 may preserve clues about the formation of the galactic bulge, or remnants of ancient structures that helped build our galaxy. In other words, the neighbourhood containing our fastest spinner may itself be a historical archive. Some addresses carry prestige. This one carries archaeology. There is another practical challenge in observing Terzan 5. It lies in a crowded direction toward the galactic centre, where dust and many foreground stars complicate observation. Dense stellar fields can make optical studies difficult. Radio astronomy helps pierce some of these obstacles, though it brings its own technical demands. Again, nature does not simply hand over treasures, it asks effort. That effort has paid off. Terzan 5 has become famous for hosting numerous pulsars. When astronomers study it, they're exploring not one curiosity, but an ecosystem of compact objects and dynamic stellar histories. PSR J1748-2446 AD is perhaps the celebrity resident, but it is not the only interesting neighbour. Imagine a city where several Nobel Prize winners, inventors, acrobats, and eccentric clockmakers all live on the same block. That gives some sense of a rich globular cluster. Now let us return to the discovery itself for a moment. When a new pulsar candidate appears in data, astronomers do not immediately declare victory. They verify repeatability. They refine timing solutions. They ensure the signal is celestial rather than human-made interference. They test whether orbital motion is shifting arrival times. They measure period accurately. For a record holder like PSR J1748-2446 AD, caution matters even more. Extraordinary claims deserve careful checking, not because skepticism is joyless, but because precision protects wonder. Once confirmed, the result becomes stronger than excitement alone. It becomes knowledge. There is a lovely discipline in that process. Science does not ask us to suppress amazement. It asks us to support amazement with evidence. And when the evidence holds, amazement deepens. Now think of the contrast. Inside Terzan 5, stars crowd together under ancient gravity. Among them, a neutron star smaller than a city rotates hundreds of times each second. From Earth, separated by thousands of light years, researchers detect subtle radio pulses and infer its behaviour with equations and instruments. That is one of the grand achievements of the human mind, to know distant invisible things accurately. We often underestimate how astonishing this is because modern technology feels normal once it works. But pause with it. we can identify a compact remnant in a dense cluster across the galaxy and measure how many times it spins each second. That should never feel entirely ordinary. There is also something emotionally comforting in the way discovery often happens, not through one heroic glance, through collaboration, engineering, observation, correction, patience, repeated attempts. Many truths arrive this way, quietly, through sustained attention. PSR J1748-2446 AD is a record holder, yes, but it is also a monument to listening carefully enough. Now that we know where this star lives, another question naturally follows. What would it be like inside a globular cluster itself, where stars crowd the sky, encounters are common, and ancient systems keep evolving in close quarters? Step outside on a clear night from a dark place on Earth, and the sky can already feel generous. Thousands of visible stars if conditions are right. The pale band of the Milky Way crossing overhead. Familiar constellations pretending they were designed for us. Enough light points to inspire myths, navigation, poetry, questionable smartphone photography, and long, thoughtful silences. Now imagine that view becoming far more crowded. Imagine stars not scattered with roomy distances between them, but gathered densely in every direction. Imagine bright points so numerous that darkness itself seems to have less space available. Imagine living in a region where neighbouring stars are much closer on average than the Sun's nearest stellar companions are to us. That is the sort of environment a globular cluster can offer. PSR J1748-2446 AD lives in Terzan 5, one of the Milky Way's most intriguing dense stellar systems. To understand the life of our record-holding pulsar, we need to understand its neighbourhood, because places shape stories, and globular clusters are places where stars lead unusually social lives. A globular cluster is a roughly spherical collection of stars bound together by gravity. Many contain hundreds of thousands of stars, some contain more. They orbit galaxies as ancient companions, often residing in halos or toward intergalactic regions depending on the system. Most are very old, among the oldest surviving stellar populations associated with galaxies like our own. If the Milky Way is a vast city, globular clusters are ancient fortified districts still circling after immense spans of time. They are dense, durable, and full of history. Our local region of the galaxy is comparatively spacious. The nearest star system beyond the Sun, Alpha Centauri, lies over 4 light-year away. That is close by galactic standards, but still an enormous distance. If the Sun were a house, the nearest stellar neighbour would be another house many trillions of kilometres away. Stars near us are not bumping elbows. They have personal boundaries. Inside a globular cluster core, average distances between stars can be much smaller. Exact values vary by cluster and location within it, but stars may be separated by fractions of a light-year or less in dense central regions. That is still a large distance by human standards, yet dramatically tighter than what we experience locally. Space remains spacey. It is simply less extravagant with spacing. From a planet somehow surviving stably in such an environment, the night sky could be astonishing. Numerous stars would appear brighter. Multiple brilliant neighbours might outshine anything we know except the Sun. Constellations would be less tidy because the sky would be crowded with candidates. You might spend evenings saying, "Which bright one did you mean?" Navigation apps would struggle. Darkness, however, would still exist. Even dense star fields do not turn the sky into daylight. Distances remain vast. But the emotional sense of cosmic loneliness would likely be reduced. A globular cluster sky would feel inhabited. Now, let us talk about age. Globular clusters are old, very old. Many formed more than 10 billion years ago, not long after the early eras of galaxy formation. They are living archives of the ancient universe. Their stars preserve clues about chemistry, stellar evolution, and the history of the Milky Way. When we study a globular cluster, we're not just looking at many stars, we're reading an old neighbourhood ledger. Terzan 5 is particularly interesting because it does not fit every simple expectation. It has shown evidence of multiple stellar populations and unusual chemical complexity, suggesting a rich and perhaps special history. Some astronomers have proposed it may be a relic of primordial structures involved in building the galactic bulge. In short, this is not just any crowded cluster, it may be a survivor with stories, and somewhere within it spins PSR J1748-2446 AD. Now, why do crowded places matter for pulsars? Because gravity becomes social. In a sparse region, stars mostly evolve according to their original pairings and internal properties. In a dense cluster, close encounters become more likely over immense timescales. Stars can perturb each other. Binary systems can be altered. Companions can be exchanged. Orbits can tighten. Encounters can fling objects outward or draw them inward. The cluster becomes a long-running dance floor with no music humans can hear and choreography written in Newtonian gravity. This matters especially for compact objects like neutron stars. A neutron star in a dense cluster may capture or retain a companion more easily than in emptier space. Binary systems involving neutron stars can become crucial because a companion may transfer matter onto the neutron star, spinning it up into a millisecond pulsar. That likely helps explain why globular clusters host so many millisecond pulsars relative to their size. They are efficient workshops for making them. PSR J1748-2446 AD may be a speed champion, but champions often come from strong training environments. Terzan 5 is one such environment. Now picture daily life for stars there, if stars had opinions. Noisy neighbourhood, bright neighbours, frequent long-term gravitational awkwardness, complicated relationships, ancient residents who never move away. It sounds less like empty space and more like a cosmic apartment complex with excellent views and no privacy. Of course, stars do not gossip, though binary interactions sometimes feel close. There is another important feature of globular clusters: mass segregation. Over time, through countless gravitational interactions, heavier objects tend to drift toward the centre, while lighter ones may migrate outward. This is not conscious sorting, but statistical dynamical evolution. Dense remnants such as neutron stars and white dwarfs can become concentrated in central regions. That means the cluster core can be especially rich in interesting remnants. Where many people see a fuzzy ball of stars, dynamicists see a bustling ecosystem of mass exchange, orbital reshuffling, and long-term structural evolution. Again, hidden complexity beneath calm appearance. A recurring theme tonight. Now, imagine the timescales. Human cities rise and change over centuries, forests over centuries or millennia. Globular clusters evolve over billions of years. Encounters that are common in cluster terms may still require immense patience by human standards. A close interaction might happen after spans longer than civilization has existed. Yet given enough time, rare events become expected events. The universe uses abundance of time the way we use convenience. Need something unlikely? Wait 1 billion years. This helps us emotionally recalibrate probability. In daily life, unlikely means perhaps never. In stellar systems with billions of years available, unlikely often means eventually. That is why dense clusters can manufacture exotic systems. Now, what about planets? Could planets exist in globular clusters? In principle, planets can form in many environments, but dense stellar neighbourhoods may pose challenges. Close stellar passages can perturb planetary orbits. Radiation environments may differ. Long-term stability could be more complicated in central crowded zones. Still, the universe has a habit of exceeding cautious expectations, so one should never say never too confidently. If a planet did enjoy a stable orbit in such a cluster, its night sky might inspire either spiritual serenity or total distraction. Productivity could suffer. Now let us bring the focus back to PSR J1748-2446 AD specifically. As a millisecond pulsar in Terzan 5, it likely benefited from the cluster's crowded conditions. Somewhere along its history, binary evolution probably allowed mass transfer from a companion. Matter spiraled inward, delivering angular momentum and accelerating the neutron star to extraordinary spin rates. That kind of pathway is much easier to imagine in a dense cluster, where binaries are common and interactions reshape systems. So when we say this star lives in Terzan 5, we are not naming a location casually, we are naming a cause. Environment matters. This is true in astrophysics and nearly everything else. A violin in a cupboard makes less music than one in practiced hands. A seed on stone grows differently than one in soil. A neutron star in sparse isolation may live one life. A neutron star in Terzan 5 may become the fastest known spinner. There is also beauty in the visual appearance of globular clusters from afar. Through telescopes, many appear as glittering spheres, dense toward the centre, stars resolving outward like grains of frost. They are among the most elegant objects in observational astronomy. Graceful outside, complicated inside. Also, a recurring theme. Some of the oldest things in our galaxy are not crumbling ruins, but bound stellar communities still intact after immense time. That persistence can feel reassuring. Structures can endure if gravity and circumstance allow. Globular clusters have survived galactic tides, internal interactions, stellar deaths, and epochs beyond ordinary imagination. They remain. Terzan 5 remains, and within it, PSR J1748-2446 AD keeps spinning. Hundreds of rotations each second amid neighbours older than many landscapes on Earth. That image is worth resting with. An ancient cluster, crowded and patient. A tiny remnant star, fast beyond intuition. Signals crossing the galaxy, humans noticing. There is another subtle comfort here. We often think crowded places must be chaotic, yet clusters maintain structure. Thousands or hundreds of thousands of stars move under gravity without immediate catastrophe. Paths cross in influence more often than near us, but not in cinematic collisions every afternoon. Complexity does not always mean disorder. Many systems are busy and stable at once. Cities, forests, brains, globular clusters. Now, once we appreciate the neighbourhood, the next question becomes irresistible. How exactly does a companion star help turn a neutron star into a millisecond pulsar? Not every record in the universe is earned alone. Some are built quietly through partnership, timing, persistence, and a steady supply of help arriving over very long periods. That is especially true for many millisecond pulsars, including likely PSR J1748-2446 AD. However dramatic its current spin may seem, the star may owe much of that speed to a companion orbiting nearby. This part of the story is one of astronomy's most elegant reversals. We often imagine dead stars as isolated remnants, drifting in silence after their main lives are over. Yet many neutron stars remain in binary systems, gravitationally linked to another star. In those pairings, the companion can become transformative, not through conversation, not through encouragement, though both would be kind, through matter. To understand how this works, picture two stars orbiting a shared centre of mass. One has already gone through its violent collapse and become a neutron star, tiny, dense, and perhaps spinning moderately fast. The other remains a more ordinary star, still containing outer layers of gas held loosely compared with the neutron star's extraordinary compactness. As the companion ages, it changes. Stars do not stay the same. They expand, brighten, rearrange interiors, and in some stages swell significantly. If the companion grows large enough, Its outer layers may extend into a region where the neutron star's gravity can begin to capture material. This critical region is often described using the Roche lobe, a gravitational boundary around each star in a binary system. If one star expands beyond its lobe, gas can spill toward the other. That phrase, spill toward, sounds gentle. Reality is more dramatic. Gas streams away from the companion under gravity, drawn toward the neutron star. But it does not usually fall straight in like a dropped pebble. Because the stars are orbiting and the gas carries angular momentum, the material tends to form an accretion disk around the neutron star. A disk is nature's preferred compromise when gravity wants inward motion and momentum wants sideways motion. You see disks in many places: rings, planetary systems, black hole-feeding structures, protoplanetary nurseries. Spin and gravity together often produce circles before endings. So now imagine a neutron star wrapped in a hot, swirling disk of stolen or donated gas. Depending how sympathetically one views the companion, that material gradually spirals inward, and as it does, it transfers angular momentum. This is the key. The incoming gas acts like countless tiny pushes in the correct rotational direction. Over time, these pushes accelerate the neutron star's spin. Slowly, steadily, over immense timescales, the remnant star turns faster and faster. This process is called recycling. A neutron star that may have slowed after birth can be spun back up into a millisecond pulsar. That name, recycled pulsar, is wonderfully practical. It suggests an old object given renewed usefulness through fresh input. There are worse metaphors for life. PSR J1748-2446 AD likely belongs to this category. Its astonishing rotation rate of roughly 716 times per second is difficult to explain as a simple leftover from birth alone. The more likely story is a neutron star that survived collapse, entered or remained in a binary partnership, then accreted matter long enough to reach extraordinary speed. So when we admire the fastest known spinner, we may also be admiring one of the galaxy's great long-term collaborations. Now let us slow the process down in imagination. A little gas leaves the companion. It joins the disk. The disk heats through friction and compression. Material spirals inward. A little angular momentum is transferred. The neutron star spins slightly faster. Repeat this not for a weekend, not for a season, but perhaps for millions or billions of years. Tiny changes become transformation. That pattern appears everywhere. Water shapes stone. Practice builds skill. Savings build slowly. Stars accelerate one grain of gas at a time. The universe often prefers accumulation to drama, even when producing dramatic results. There is also something deeply satisfying about the efficiency of it. A neutron star is already compact, already primed to rotate quickly. It simply needs additional angular momentum. The companion star, through orbital mechanics and mass transfer, supplies exactly what is needed. Cosmic engineering with no committee meetings. Now you might reasonably ask whether the companion enjoys this arrangement. That depends on your definition of enjoy. Mass transfer can significantly alter the donor star. It may lose outer layers, shrink, become stripped, or evolve into a faint remnant. Some companions to millisecond pulsars are reduced to very low masses. In certain systems, pulsar radiation can even ablate material from the companion, gradually eroding it. Astronomers have given some of these systems colourful names such as Black Widow and Redback Pulsars. Science occasionally permits drama in naming, so binary life can be complicated. Supportive, yes, also intense. In the case of PSR J1748-2446 AD, observations indicate it is in a binary system, reinforcing the recycling picture. The neutron star did not simply spin itself into fame, it likely had company. This matters because it changes how we think about extreme objects. We often credit the object alone, the fastest star, the brightest source, the most massive remnant. But many extremes are relational outcomes. Context matters, environment matters, partners matter. That is true in star clusters and elsewhere. Now imagine the view, impossible though it is, from near the companion star during the active accretion era. Nearby, a tiny neutron star circles with immense gravity. Gas from your outer layers is drawn away into a glowing disk. X-rays may blaze from heated infalling matter. The compact remnant grows faster in spin with each passing age. It would not feel like a quiet retirement, yet from that difficult arrangement comes scientific treasure. Accreting neutron stars teach us about gravity, dense matter, magnetism, disk physics, thermonuclear bursts, and spin evolution. Even stellar inconvenience can be educational. There's another subtle point worth appreciating. Why does the gas not simply crash in randomly and cancel itself out? Because orbital systems have direction. Matter in the disk shares organised motion. The angular momentum is coherent enough that the net effect can accelerate the star rather than merely create chaos. Disks are messy in detail, but orderly in broad behaviour. Again, complexity and structure coexist. This is one of nature's favourite themes. Now let us consider time. Humans are impressed by sudden acceleration. Fast cars, quick reflexes, overnight success stories that usually took 10 years in secret. But PSR J1748-2446 AD's speed was likely built over immense spans through persistent transfer. That can be oddly comforting. Not every astonishing result comes from explosive beginnings. Some come from long, steady addition. The star became extraordinary gradually. Many worthwhile things do. There is also a graceful irony here. The neutron star is tiny and dense, yet dependent on something larger and less extreme for its record-setting spin. The companion, a more ordinary star, may have supplied the fuel for exceptionalism. Ordinary contributors are often underrated. Without support staff, many triumphs vanish. Without companions, some pulsars stay slow. Now, can the process continue forever? No. Mass transfer changes conditions. The donor star can lose too much material. Orbital parameters evolve. Magnetic effects matter. Spin-up reaches limits. Eventually the active feeding phase may end. What remains is a rapidly rotating millisecond pulsar, now observable as a precision beacon. The construction phase stops. The clock remains. That is rather elegant. Years of messy work behind the scenes, then visible precision. You can say the same of cathedrals, musicians, and many breakfasts. By the time we observe PSR J1748-2446 AD as a radio pulsar, much of the transformative history may already be over. We are seeing the polished result, not the long labour that created it. Science often works this way. We infer history from present clues. A canyon reveals water. Wrinkles reveal time. A millisecond pulsar reveals accretion. Now, because this star lives in a dense globular cluster, the chances of forming and preserving interesting binaries are enhanced. Terzan 5 is exactly the sort of place where stellar relationships become frequent enough to generate unusual outcomes. In a quieter neighbourhood, perhaps this object would have had a different fate. Place plus partner plus time. That combination can do remarkable things. There's also an emotional lesson hidden here if one wants it stated plainly. Being changed by another is not always loss. Sometimes it is growth. Sometimes it is speed. Sometimes it is the difference between ordinary rotation and becoming one of the fastest known stars in the galaxy. Of course, binary systems can also be unstable, difficult, and destructive. So let us not become sentimental too quickly. Still, cooperation under gravity has produced wonders. If a companion can keep spinning a neutron star faster and faster, why does the process stop where it does? Why not 1,000 spins each second or more? What prevents nature from pushing indefinitely upward? Look up at the night sky long enough, and it is easy to imagine stars as solitary things. Each one appears as a single point, separate, independent, self-contained, a distant lamp with no need of neighbours. That impression is understandable from Earth, where distance compresses complexity into dots. But many stars are not alone. In fact, a large fraction of stars belong to pairs or larger systems. They orbit one another, exchange influence, sometimes exchange matter, and shape each other's futures in ways a solitary star never experiences. The universe, it seems, is quite fond of partnerships. PSR J1748-2446 AD likely owes much of its remarkable speed to such a partnership. So tonight we pause from dramatic spin rates and dense matter for a quieter but essential subject: binary systems, the gravitational relationships that can turn an already strange object into a record-setting one. A binary star system is simply two stars bound by gravity, orbiting a common centre of mass. That centre is not always exactly inside one star. If one object is much heavier, the balance point lies closer to it. If the two are similar in mass, the centre may sit between them. This means binary stars do not behave like one star dragging another around behind it. They dance together. Some dances are graceful and wide, some are tight and rapid, some become messy enough to interest generations of astronomers, and some eventually produce millisecond pulsars. Now, if you could watch a binary system from a comfortable and impossible vantage point over millions of years, you would notice something important. Stars are not rigid marbles. They evolve. They swell, contract, lose mass, brighten, dim, collapse, and age. So a binary system is not just two objects orbiting each other in static harmony. It is two changing objects affecting one another over time. That makes binary systems rich with possibility. Suppose two stars form together from the same cloud of gas. One is more massive than the other. The heavier star burns fuel faster and evolves sooner. It may become a giant star, then collapse in a supernova, leaving behind a neutron star. Meanwhile, the lighter companion continues living a more ordinary stellar life. Already the pair has become unusual. One member is a compact remnant with immense gravity. The other is still a normal star. Now continue the clock forward. The companion ages and expands. If it grows large enough, outer gas can drift beyond its gravitational comfort zone and toward the neutron star. Matter forms an accretion disk. Angular momentum transfers. The neutron star spins up. This is the pathway we discussed previously. But it only happens because the binary relationship exists. Without the partner, no transfer. Without transfer, likely no extreme spin. So although PSR J1748-2446 AD gets the attention, the companion deserves a respectful nod. Records often have assistants. Now let's explain a useful concept gently. The Roche lobe. Every star in a binary system has a region around it where its own gravity dominates nearby material. If a star expands enough to fill this region, gas near the boundary can more easily flow toward the companion. Think of two hills with a saddle between them. A marble near the top of one hill rolls inward. A marble near the saddle may cross over. Gas behaves more fluidly than marbles, of course, but the analogy helps. Once a star fills its Roche lobe, mass transfer can begin, and once mass transfer begins, futures change. This process may be stable and gradual, or more dramatic depending on masses, separation, and stellar states. Binary evolution can be one of the most complicated branches of stellar astrophysics, because there are many possible pathways. Stars can widen apart, they can spiral closer, they can swap mass, they can strip one another's envelopes, they can merge, they can leave remnants in surprising combinations: white dwarf with white dwarf, neutron star with a normal star, black hole with star, compact remnant with another compact remnant. The universe keeps varied company. Now imagine two people trying to dance while both are changing height, weight, shape, and momentum mid-song. That begins to capture why binary calculations can be challenging. Yet from complexity comes treasure. Type 1, a supernovae, X-ray binaries, gravitational wave mergers, cataclysmic variables, millisecond pulsars, and many other phenomena rely on binary evolution. If solitary stars are important, paired stars are often where the plot thickens. There is also a psychological comfort in this cosmic truth. We often tell stories of lone brilliance, the isolated genius, the self-made success, the independent force. Reality is usually more relational. Systems matter, support matters, timing matters, context matters. Stars appear to agree. Now let us bring this back to Terzan 5, the dense globular cluster where PSR J1748-2446 AD resides. Crowded environments make binaries especially interesting. Close encounters with passing stars can alter orbits, exchange companions, or harden binaries by tightening them. Over billions of years, these interactions can create systems unlikely to arise in quieter neighborhoods. So the quiet partner of PSR J1748-2446 AD may not only have fed it, the cluster itself may have helped arrange the meeting or preserve the partnership. Sometimes even relationships need infrastructure. There is another subtle point about companions in such systems. The companion star may eventually become faint, stripped, or difficult to detect compared with the pulsar's significance. Public attention goes to the fast spinner. The donor fades into technical notes. This too feels familiar. Some contributors disappear behind outcomes they made possible. Yet scientifically, the companion remains central to the explanation. When astronomers identify a millisecond pulsar in a binary orbit, they gain opportunities. Orbital timing can reveal masses. Tiny delays in pulse arrival times can map motion. Relativity may become measurable. Companion properties help reconstruct history. The partnership becomes a laboratory. Two stars orbiting each other can teach us more than one star alone. Now let us imagine the orbital rhythm. While PSR J1748-2446 AD spins hundreds of times each second, it also orbits its companion over a much longer period. So there are two clocks operating at once: the rapid internal clock of rotation, the slower shared clock of orbit. This layered timing is common in astronomy. Moons orbit planets that rotate, while planets orbit stars that rotate, while stars orbit galactic centers. The cosmos enjoys nested rhythms. Perhaps that is one reason it feels soothing to think about at night. There is order within order. Now, do binary systems always remain peaceful? Not remotely. Mass transfer can destabilize. Supernova kicks can disrupt pairs entirely. Tidal forces distort stars. Radiation from pulsars can erode companions. Mergers can occur. Some systems become violent X-ray sources. Others end in explosions. The term quiet partner tonight refers less to emotional serenity and more to observational fame. One member gets headlines, the other did crucial work. Still, many binary phases can be long and relatively stable on astronomical timescales. Enough stability exists for millions of years of spin-up. That patience matters. PSR J1748-2446 AD was not rushed into its record. It was prepared. Now think about what the companion may have experienced. A normal star aging naturally, then finding outer layers drawn toward a compact neighbour with crushing gravity. Material leaves, forms a disk, radiates energy, and changes both stars' future paths. It is not the retirement plan most stars would choose. Yet from this difficult arrangement emerges one of the galaxy's finest clocks. That recurring cosmic pattern deserves notice. Stress can generate structure. Interaction can generate novelty. Loss in one place can create wonder in another. We should be careful with metaphors here, but the broad lesson is real. Now another important fact. Many stars we call single may once have had partners or still do in ways hard to observe. Distance, brightness, contrast, orientation, and limited instruments can hide companions. The night sky looks simpler than it is. Again, dots conceal stories. PSR J1748-2446 AD reminds us of that beautifully. To the public, it is the fastest spinner. To astrophysics, it is likely the outcome of binary evolution, cluster dynamics, dense matter physics, magnetic behavior, and long-term timing. One object, many causes. That is often how reality works. There is also elegance in the mathematics of binaries. From orbital periods and timing shifts, astronomers can infer masses and separations of bodies never visited. Tiny delays in pulses caused by changing distance or relativistic effects become clues. A star pulses. The pulses arrive early or late by tiny amounts. From that, humans calculate invisible orbits across the galaxy. That should never feel boring. It is detective work of a very high order. If matter from a partner can keep spinning a neutron star faster and faster, what eventually says enough? Why does nature stop near certain speeds rather than allowing endless acceleration? Once you learn that a star can spin around 716 times every second, the next thought often arrives immediately. Why stop there? Why not 1,000 times each second? Why not 5,000? Why not so fast that numbers lose all personality and become pure alarm? It is a fair question. If PSR J1748-2446 AD has already reached what sounds like an impossible speed, why does the universe not simply continue upward? The answer is one of the most satisfying in science, because everything has constraints, not always obvious ones, not always gentle ones, but real systems live inside boundaries set by structure, energy, stability, and the laws that govern matter. Speed records are interesting precisely because they approach those boundaries. PSR J1748-2446 AD is not merely fast, it is informative. Its existence tells us something about what neutron star matter can survive. To understand why there is a limit, imagine swinging a bucket of water in a circle overhead. If you move it fast enough, the water stays inside because it is continually being redirected along the circular path. Slow too much, and gravity wins. The water falls out, the floor becomes involved, and trust is reduced. Circular motion requires inward force. For planets orbiting stars, gravity provides that force. For material on a spinning neutron star's surface, gravity and internal structural forces must keep matter bound, while rotation tries, in effect, to fling equatorial material outward. The faster the spin, the harder that job becomes. At low rotation rates, no problem. At very high rotation rates, the contest becomes serious. Eventually, if the star spins too quickly, matter near the equator could begin to break free, or the star could become unstable. This threshold is often called the mass-shedding limit or breakup limit. The name is admirably direct. Spin too fast, start losing mass. That is not ideal for maintaining records. Now, let us picture the geometry. A rotating body experiences stronger outward inertial effects at the equator than near the poles. That means the equator is the most vulnerable region. As spin rises, the star can bulge outward there, becoming slightly oblate rather than perfectly spherical. Earth does this mildly. Jupiter does it more noticeably. A neutron star doing it at hundreds of spins per second enters far more dramatic territory. The star reshapes itself in response to rotation, and shape matters, because once the equator extends farther from the centre, keeping matter bound becomes even more demanding. Nature starts charging higher rent for every extra turn. This is why faster is not free. Now, if neutron stars were made of simple rigid metal, we might estimate limits one way, but they are not. They are objects of ultra-dense matter governed by gravity, nuclear physics, relativity, and quantum effects. Their internal composition influences how much mass they can support, how large they are, and how quickly they can rotate before trouble begins. This means the maximum spin rate depends on the equation of state of neutron star matter. That phrase sounds technical, but the idea is simple. How does matter behave when crushed to extraordinary density? Is it relatively stiff, resisting compression strongly? Is it softer, compressing more easily? Different answers produce different radii and different rotational limits. So when astronomers observe an object like PSR J1748-2446 AD spinning stably at around 716 Hz, they gain clues. Some models of dense matter become more plausible, others face pressure. The star becomes a laboratory for invisible physics. That is one reason record holders matter. Now let us ask a practical question. Why has no confirmed pulsar been found spinning much faster? There are several possible reasons. One is that nature rarely produces them. Another is that such objects may exist but are difficult to detect. A third is that accretion spin-up processes may naturally stall before reaching much higher rates. And all three could be partly true. Let us take them one at a time. First, production. To create an ultra-fast millisecond pulsar, you need a neutron star in a suitable binary system, enough transferred matter, enough angular momentum, and long-term stability. Not every neutron star gets such conditions. Many never receive the opportunity. Second, detection. Very fast pulsars can be observationally challenging. Signals may be faint. Binary motion can smear timing signatures. Interstellar material can disperse pulses. Survey methods have limits. The universe occasionally hides its best tricks behind technical inconvenience. Third, natural braking. Even while accretion spins a neutron star up, other processes can counteract acceleration. Magnetic torques may matter. Emission of radiation carries energy away. Internal oscillations may develop. Gravitational wave emission has been proposed in some scenarios if the star has slight asymmetries or unstable modes. In short, the star may gain speed and lose speed simultaneously through different channels. Eventually an equilibrium may emerge. Push meets resistance. Growth meets drag. Records stop rising. This should sound familiar. It applies to bicycles, careers, metabolism, and stars. Now let us linger on gravitational waves for a moment, gently. If a spinning object is perfectly symmetric, it does not radiate gravitational waves strongly just from steady rotation alone. But if it has tiny bumps, deformations, or certain internal oscillations, then rapid spinning can generate ripples in space-time that carry away energy and angular momentum. A neutron star does not need to be lumpy in any everyday sense. Even minuscule asymmetries matter at extreme speeds. So one possibility is that some neutron stars trying to spin faster may shed rotational energy through gravitational radiation. The universe apparently has subtle breaks. There is something elegant about that. Nature often prevents extremes not by one dramatic wall, but by many quiet frictions. Now consider another factor. Accretion itself can end. The companion star may lose too much mass. The orbital configuration may change. Mass transfer can weaken or stop. Once the fuel for spin-up fades, the neutron star is left near whatever speed it reached, after which long-term slowing processes gradually take over. So even if a system might have gone faster eventually, opportunity may run out first. Timing matters. Again, a universal theme. Now, could something spin much faster than PSR J1748-2446 AD in principle? Possibly yes. Theoretical neutron star limits can exceed 716 Hz, depending on mass and internal physics. Some models allow over 1000 Hz before breakup, but allowed in principle is different from commonly produced in nature, and different again from observed clearly by humans. Reality is full of gaps between possible, probable, and detected. That distinction is worth remembering in all fields. Now let us make the speed intuitive again. At 716 rotations per second, each turn takes about 1.4 milliseconds. That means by the time you finish reading a short word, the star may have completed several rotations. Push much faster, and periods become fractions of a millisecond. The engineering of nature becomes ever more demanding. Material at the equator races faster. Centrifugal stresses grow. Magnetic and relativistic effects intensify. Tiny instabilities matter more. This is why extra speed becomes increasingly expensive. There is another philosophical comfort hidden here. Limits make meaning. If anything could go infinitely fast, records would be dull. If systems had no constraints, achievement would lose context. Boundaries are what allow comparison, tension, and understanding. A mountain is impressive because gravity exists. A marathon matters because fatigue exists. A Pulsar record matters because breakup exists. Constraint gives shape to excellence. Now, PSR J1748-2446 AD sits in a particularly interesting region of possibility. It is fast enough to challenge theory, yet stable enough to exist. That combination makes it scientifically precious. Too slow, and it tells us less. Too fast to survive, and it tells us nothing because it would not be there. Near the edge is where lessons gather. Nature often teaches best at thresholds. Water near freezing, matter near collapse, stars near spin limits, humans near bedtime, occasionally. Now let us imagine if the star were nudged faster somehow. A little more spin, a little more equatorial bulge, a little more strain on bound surface layers. Perhaps more efficient braking processes activate. Perhaps mass begins to shed. Perhaps internal modes grow unstable. The exact story depends on details we still study. That uncertainty is exciting. Even after decades of pulsar astronomy, dense matter still keeps secrets, and PSR J1748-2446 AD helps us ask better questions. There is also humility in realizing that a tiny object the size of a city can constrain theories about nuclear matter more effectively than many laboratories on Earth. We cannot recreate full neutron star interiors in terrestrial conditions, but the cosmos runs experiments at scale continuously. Astronomers simply observe the results. A distant star spinning quickly can tell us what matter permits. That is extraordinary. Beneath the astonishing spin, beneath the lighthouse pulses, beneath the record-setting number that first captures attention, there is a quieter mystery hidden inside PSR J1748-2446 AD. What is it made of? And perhaps even more importantly, what keeps it from collapsing further? These are not small questions. They reach into some of the deepest unsolved areas of physics, because a neutron star is not held up the way ordinary stars are held up, and it is not built from matter behaving in ordinary ways. Our sun remains stable because hot gas pressure from nuclear fusion pushes outward against gravity pulling inward. As long as fusion continues in the core, that balance can persist for billions of years. But a neutron star is different. Its main fusion life is over. The original star exhausted its central fuel, collapsed catastrophically, and left behind a compact remnant. There is no sun-like furnace at the centre providing the same outward support, yet the object still exists. It does not simply continue collapsing into nothing smaller, so something else must resist gravity, and gravity here is formidable. Imagine more mass than the sun packed into a sphere perhaps 20 kilometres across. Gravity at the surface becomes immense. Every layer presses on the layers below it. The deeper you go, the pressure rises to values almost absurd beyond human intuition. If earthly pressures are books on a shelf, neutron star pressures are mountains stacked on mountains, then asked to stand closer together. So why does the star not keep falling inward? The first answer comes from quantum mechanics. Specifically, a principle called the Pauli exclusion principle. This rule says certain particles, called fermions, cannot all occupy the same quantum state simultaneously. Electrons are fermions, neutrons are fermions, protons too. That may sound abstract, but it has concrete consequences. Matter cannot simply compress indefinitely, while keeping particles arranged however gravity prefers. Quantum rules create resistance. In white dwarfs, electron degeneracy pressure helps support the star. Electrons resist being squeezed into identical states. That pressure can hold up the remnant of a lower mass star, but if the remnant is too massive, electron support is no longer enough. Collapse continues. Electrons are forced into protons, neutrons form, and then a neutron star is born. Now, neutron degeneracy pressure enters the story. Neutrons, also being fermions, resist being packed arbitrarily into the same states. This creates a powerful quantum pressure even at low temperature. It does not depend on heat the way gas pressure does. It arises because of the structure of matter itself. That is one reason neutron stars are so remarkable. They are supported partly by the fact that particles refuse to be arranged carelessly. The universe contains rules of occupancy. Even gravity must negotiate with them. But neutron degeneracy pressure is not the whole answer. At the immense densities inside a neutron star, the strong nuclear force also becomes crucial. This is the force that binds atomic nuclei together. At certain distances, it is attractive. At extremely short separations, it becomes strongly repulsive. That repulsive behavior matters enormously. As neutrons are squeezed closer and closer, nuclear interactions resist further compression. So what holds up a neutron star is not one simple mechanism, but a combination of quantum degeneracy effects and nuclear forces operating under extraordinary conditions. Gravity pushes inward. Quantum structure and nuclear physics push back. A balance forms. That balance is the star. There is something elegant about this. The object is not a solid ball in the ordinary sense. It is an ongoing truce between colossal inward pull and microscopic laws refusing surrender. Now let us descend layer by layer, carefully. The outermost region is the crust. Even the crust is exotic compared with the Earth materials. Atomic nuclei exist in a lattice immersed in a sea of electrons. Pressures are already extreme. As depth increases, nuclei become more neutron-rich because electrons are forced into protons. Go deeper, and the structures may become bizarre enough that physicists nickname them nuclear pasta. This is not a joke, though it sounds like one. Under competing forces, matter may arrange into sheets, rods, tubes, and blobs resembling shapes humans associated with lasagna, spaghetti, gnocchi, and related carbohydrates. The universe occasionally rewards researchers with naming opportunities. Why do these forms appear? Because matter is trying to minimize energy under bizarre constraints. Attractive and repulsive forces compete. Geometry becomes strategy. Even in extreme conditions, structure emerges. Below that crust lies denser interior matter where separate nuclei may dissolve into a fluid dominated by neutrons, along with some protons, electrons and other particles depending on depth and model assumptions. And then we reach the core. This is where certainty becomes more cautious. We know the core is extremely dense. We know pressures are enormous. We know gravity is relentless. But the exact state of matter there remains one of astrophysics' great open questions. Possibilities include hyperons, particles containing strange quarks, meson condensates, deconfined quark matter, where neutrons and protons themselves break into constituent quarks moving more freely, mixed phases of several forms, or something we have not yet fully described. That last possibility should always remain available when dealing with nature. Reality has a history of exceeding categories, so when we ask what is inside PSR J1748-2446 AD, the honest answer is partly known and partly under investigation. That honesty is a strength of science. We know much. We know where uncertainty begins. Now let us connect this to spin. PSR J1748-2446 AD rotates around 716 times each second. That speed adds another layer of stress. Matter in the star is not only resisting gravity, it is also arranged in a rapidly rotating body where equatorial regions experience strong centrifugal effects. So the internal matter must support both immense self-gravity and the structural demands of rapid spin. That makes this pulsar especially valuable scientifically. If it can rotate stably at such speed, certain models of dense matter become more plausible, others become harder to maintain. A fast pulsar is not merely exciting, it is evidence. Now consider temperature. Newborn neutron stars are extremely hot by human standards, but over time they cool. Yet even when cooler thermally, degeneracy pressure remains. This pressure does not disappear when heat fades, because it is rooted in quantum occupancy rules rather than thermal agitation. That means a neutron star can remain supported long after its fiery birth has settled. Quiet outside, unusual inside. Another recurring theme. There is also a mass limit. If enough mass is added, even neutron star support may fail. Then gravity can win further, potentially producing a black hole. The exact maximum mass depends on the same uncertain equation of state we seek to understand. So neutron stars live in an extraordinary middle ground. Too little mass, and you might have a white dwarf instead. Too much mass, and collapse continues. In between lies one of nature's strangest stable objects, balanced on the edge of deeper possibilities. There is something emotionally resonant in that. Many meaningful things exist in middle grounds: coastlines, twilight, adolescence, negotiation, ecosystems between extremes. Neutron stars too are threshold objects. Now imagine holding a sphere the size of a city containing solar-scale mass, supported by invisible quantum principles and nuclear repulsion, spinning hundreds of times each second, pulsing beams into space. That is not science fiction, that is astrophysical inventory. And yet most nights, the star simply continues existing, unnoticed by nearly everyone. The universe is full of masterpieces with poor publicity. Now why can't we just recreate neutron star cores in a lab? Because the densities, sustained pressures, and macroscopic gravitational confinement are beyond ordinary terrestrial capability. Particle colliders probe high-energy interactions. Nuclear experiments reveal pieces of the puzzle. Heavy ion collisions offer clues. But reproducing a full stable neutron star core on Earth is another matter entirely. So we use the cosmos as our laboratory. We observe masses. We estimate radii. We study spin limits. We detect gravitational waves from neutron star mergers. We model cooling rates. We compare theory with what nature already built. That is often how astronomy works. When direct access is impossible, inference becomes the art. Now let us return to what holds it together. Not glue, not metal strength, not hidden engines. What holds it together is equilibrium. Gravity compresses. Quantum rules resist overcrowding. Nuclear forces repel at short range. Rotation modifies shape and support. All these effects settle into a workable arrangement. The star is stable not because one thing wins, but because several things balance. That can feel reassuring beyond physics. Many stable systems are balances, not victories. Bodies regulate. Ecosystems self-adjust. Relationships negotiate. Stars persist through competing forces. Now, one final subtlety. When we say solid core or matter inside, it is tempting to picture a static lump. But microscopic particles are dynamic. Fields fluctuate. Superfluidity may occur in some regions. Superconducting behavior may arise for charged components under certain conditions. Internal rotation may involve vortices in neutron superfluids. Even deep within, stillness is misleading. Complexity continues. so the interior of PSR J1748-2446 AD may include some of the strangest known states of matter in the universe, all hidden beneath a crust no wider than a city. That mystery spins quietly through the galaxy. Stand on Earth, drop a coin, and gravity seems straightforward. Things fall downward, feet stay on floors, cups prefer tables until nudged otherwise. If you jump, gravity waits patiently and wins without arrogance. It is reliable enough that most of us stop thinking about it by childhood. But Earth gives us a gentle version. Useful, comfortable, moderate. PSR J1748-2446 AD belongs to a different category entirely. Here gravity is not merely the force that keeps you from floating away. It becomes so strong that ordinary intuition begins to fail. Light loses energy escaping. Time itself changes pace. Space is curved measurably. Matter is compressed beyond everyday imagination. This is where gravity stops feeling like household behavior and starts feeling like deep geometry. Now, before we go further, let us gently update the picture many people carry. In older everyday language, gravity is described as attraction between masses. That description works well for many practical situations. Planets orbit, apples fall, satellites require planning, nothing wrong with it. But Einstein's general relativity offered a deeper view. Mass and energy tell space-time how to curve. Curved space-time tells matter and light how to move. So gravity, at its deepest level, is not simply an invisible rope pulling objects together. It is the shape of reality around mass. That sounds grand, but it leads to measurable effects. Earth curves space-time modestly. The Sun does so strongly enough to guide planetary orbits and bend passing starlight. A neutron star curves it dramatically. PSR J1748-2446 AD packs, more mass than the Sun, into something around the size of a city. That combination is crucial. Gravity near an object depends strongly on both mass and radius. Put large mass into tiny space, and the surface region becomes extreme. This is why neutron stars are such excellent laboratories for relativity, not because they are huge, because they are compact. Compactness is one of the universe's favourite ways to become serious. Now imagine approaching such a star from far away. At first, it may seem like a bright point, perhaps unremarkable against the broader field. But as distance closes, the scale becomes deceptive. You expect something star-sized. Instead, you are dealing with an object tens of kilometres across. Small target, enormous consequence. That mismatch alone would unsettle instinct. Then gravity begins to dominate experience. On Earth, if you climb a staircase, the change in gravity is tiny. Near a neutron star, moving a modest distance vertically could matter significantly. Tidal effects, differences in gravity between one location and another, become severe close enough to the surface. And surface gravity itself would be immense. If Earth's gravity is a calm manager reminding things where to stay, neutron star gravity is a full executive team with no patience for appeals. Dropping an object would be less a demonstration than a disappearance. Jumping would become a theoretical exercise. Standing safely would require technology beyond our present menu. Now let us talk about light. Photons climbing out of strong gravity lose energy. This is called gravitational redshift. Their wavelength stretches toward the redder end of the spectrum. The stronger the gravity, the more pronounced the effect. So light emitted near the surface of a neutron star arrives altered. The star changes not only motion, but the colour-energy relationship of escaping radiation. Gravity edits light on departure. That is a lovely sentence scientifically. It also means that observing neutron stars requires accounting for relativistic effects. What we receive is not exactly what was emitted in local conditions. Reality comes with travel history. Now another strange feature appears: light bending. Because space-time is curved, paths of light near massive objects are not straight in the Euclidean sense we learn with rulers and notebook margins. They follow geodesics, natural paths through curved geometry. Around a neutron star, this can be strong enough that regions of the surface partly hidden from direct line of sight may still become visible through bent light paths. In practical terms, you may see more of the star than simple geometry suggests. The object reveals around corners. That sounds like magic, it is geometry behaving honestly. Black holes are famous for dramatic light bending, but neutron stars offer significant versions too while still presenting a surface rather than an event horizon. This makes them wonderful test beds. Now let us pause on weight. People often ask, how much would I weigh there? The answer is less useful than it sounds because you would not meaningfully stand there as you do on Earth. But the broader point is that gravitational acceleration near the surface is staggeringly higher than ours. A pebble would strike with absurd violence. Your body would object before calculations finished. So when we say gravity is strong, we do not mean a bit heavier than expected. We mean the regime where matter, motion, and survival must be rethought. There is another subtle consequence: atmosphere. Neutron stars may possess extremely thin atmospheres of hot plasma or surface layers of unusual material, but not cozy, breathable skies. Gravity compresses gases tightly. Height scales become tiny. Atmospheric behavior differs radically from Earth. No gentle breeze, no clouds to watch drift, no useful weather apps. Now let us bring spin back into the story. PSR J1748-2446 AD rotates around 716 times each second. That means strong gravity and rapid rotation coexist. The star is both compact enough for severe curvature and dynamic enough for rotational effects to matter significant. Rotation in relativity can drag spacetime slightly with it, a phenomenon called frame dragging around spinning masses. It is subtle around Earth and has been measured. Around compact, rapidly rotating objects, such effects become more significant. Space itself is not an indifferent background. It participates. That idea is one of general relativity's most profound gifts. Now imagine a spacecraft, impossibly advanced and perfectly shielded, entering orbit around PSR J1748-2446 AD. You would need extraordinary precision. Orbital speeds close in would be immense, radiation hazards severe, tidal forces dangerous, timing systems would require relativistic corrections, surface pulses might sweep by hundreds of times each second. This is not scenic tourism, it is graduate-level survival. Yet scientifically, such a vantage would be priceless. One could test gravity in strong field conditions, probe magnetic geometry, measure mass and radius more precisely, and study dense matter through emitted radiation. Danger and knowledge often share borders. Now, let us notice something emotionally interesting. We speak of gravity bending reality, but in relativity, gravity is reality's shape. It is not bending some separate stage. The stage itself curves. That perspective can be calming. We often imagine life as objects moving on a fixed backdrop. Physics suggests backdrop and motion are intertwined. Space and time are active participants, not passive scenery. The universe is more integrated than intuition first assumes. That is frequently true in smaller human matters too. Now, why do neutron stars matter so much for testing these ideas? Because Earth's gravity is too weak for many strong field effects to become dramatic. The Sun helps, but neutron stars combine high mass with tiny radius, producing much more intense curvature accessible through observations. Pulse timing, X-ray emissions, orbital motion in binaries, spin rates, surface redshift signatures, each becomes a clue. PSR J1748-2446 AD, with its extreme spin, contributes to this broader effort. Even if we never visit it, its existence constrains what matter and gravity can jointly permit. The star becomes data by simply continuing to be itself, There is elegance in that. No need to perform, no need to impress. Existence under extreme conditions is enough. Now, let us return to human scale for a breath. On Earth, gravity feels ordinary because we are built within it. Bones, muscles, blood flow, balance systems, architecture, habits, sports, and tea pouring all assume 1G. We mistake familiarity for simplicity. But gravity was never simple. It was merely nearby. Travel to a neutron star in thought, and familiarity evaporates. Suddenly, gravity reshapes light, time, motion, atmosphere, and the very structure of matter. The same force that drops keys behind furniture can curve photons around a collapsed star. That range should inspire humility. There is also comfort in knowing the universe runs by continuous law across scales. The gravity of Earth and the gravity near PSR J1748-2446 AD are not separate inventions. They are different expressions of one framework under different conditions. The everyday and the extreme are related, so are we and the stars. Clocks feel trustworthy on Earth. They sit on walls, glow on bedside tables, hide in ovens, live in phones, and quietly assure us that time is one thing moving uniformly for everyone. A minute is a minute, an hour is an hour. If two watches are working properly and no one has dropped one into tea, they ought to agree. That belief serves daily life very well. It is also incomplete. Near objects like PSR J1748-2446 AD, time becomes less obedient to common sense. Gravity changes it, motion changes it, rotation complicates it further. What feels universal in ordinary settings reveals itself as local. This is one of the most astonishing lessons of modern physics. Time is not the same everywhere. It depends on where you are and how you move. Now, before panic spreads among calendars, let us reassure ourselves. In daily human life, these differences are usually tiny, small enough to ignore unless building satellite navigation systems or doing precision experiments. But near a neutron star, tiny differences become meaningful, and PSR J1748-2446 AD is exactly the sort of place where reality stops whispering and begins speaking clearly. Let us begin with gravity. According to general relativity, clocks deeper in a gravitational field run more slowly, relative to clocks farther away. This is called gravitational time dilation. The stronger the gravity, the stronger the effect. If you place one clock on a mountain and another at sea level, the higher clock ticks slightly faster. This has been measured. GPS satellites also require corrections because they are farther from Earth's gravity and moving differently than clocks on the ground. So even your phone's map owes gratitude to relativity. Now imagine replacing Earth with a neutron star. PSR J1748-2446 AD packs more mass than the Sun into an object only around city size. Gravity near its surface is immense. A clock resting near that surface would run noticeably slower compared with a clock far away from the star. Not because the clock is broken, because time itself is behaving differently there. That sentence still feels bold, even decades after confirmation. Suppose, by some impossible miracle of engineering, you hovered safely near the surface for 1 hour according to your local clock, then returned to a distant observer. More than 1 hour would have passed for them. You would have aged less during that interval, not science fiction, relativity. The exact numbers depend on altitude, mass, radius, and motion, but the principle is firm. Gravity changes time. Now let us add motion. Special relativity tells us that moving clocks also run slower, relative to stationary observers. Again, this is not a defect in clocks. It is built into space-time itself. And PSR J1748-2446 AD rotates around 716 times each second. That means matter at its equator moves at a significant fraction of the speed of light, So a clock attached to the equatorial surface experiences not only strong gravitational time dilation, but also motion-related time dilation. Gravity slows it. Speed slows it. The star is, in a sense, a double lesson. This makes neutron stars extraordinary laboratories because both major relativistic effects appear strongly in one place. Now picture two observers, one far away, drifting comfortably in deep space, one somehow stationed near the pulsar's equator. They compare clocks. They will disagree. Neither clock is wrong. Each is telling time correctly for its own path through space-time. That is the conceptual leap relativity asks of us. There is no single universal master clock ticking identically for all observers in all places. There are local times connected by geometry. Many people find this unsettling at first. It can also be freeing. Reality is richer than uniformity. Now let us keep this gentle and practical. Why do we not notice such effects every day? Because Earth's gravity is modest compared with neutron stars, and our everyday speeds are tiny compared with light speed. Relativistic differences exist, but they are extremely small in common life. Walk across the room and time dilation is not ruining your schedule. Climb stairs and gravitational time shift is not why dinner feels late. But precision instruments can measure these things, and near compact stars the effects become impossible to ignore. This is why astronomy is so valuable. It gives us environments where subtle truths become obvious. Now consider pulses from PSR J1748-2446 AD. We receive regular signals from a star rotating hundreds of times per second. Those pulses are shaped by the star's spin, gravity, motion, and the path through interstellar space. To interpret them accurately, astronomers must account for relativistic timing effects. A pulsar is not just a clock, it is a clock in curved space-time. That distinction matters. If the pulsar orbits a companion star, additional timing shifts occur. Pulses arrive early or late depending on orbital position. Signals travelling through stronger gravitational regions can experience delays known as Shapiro delay. Time itself becomes part of the measurement toolkit. This is one reason pulsars are so scientifically precious. They turn relativity into observable rhythm. Now there is another subtlety worth enjoying. Rotation can also drag space-time. A spinning massive object can slightly pull nearby inertial frames along with it. This is called frame dragging. Around Earth it is tiny but measurable. Around compact, rapidly spinning objects, stronger effects may arise. So near PSR J1748-2446 AD, space and time are not just curved by mass, they are influenced by spin. The star does not merely sit in space-time, it stirs it. That phrase is informal but emotionally accurate. Now imagine standing in a quiet room on Earth, listening to a clock tick, 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 tick. It feels universal, but the same clock placed near a neutron star would not agree with the one on your wall after comparison. Time there would flow differently relative to here. This should not make clocks suspicious, it should make them more interesting. Clocks are local truth tellers. They report their own journey faithfully. Now let's talk about aging, since this question always arrives. Could you visit a neutron star, return, and find the future advanced around you? In principle, relativity allows differential aging through gravity and motion. In practice, visiting a neutron star closely enough and safely enough is well beyond present technology, and the environment is deeply hostile. So while the physics is real, the tourism brochure remains unavailable. Still, the concept matters because it reveals what time is. Not an invisible river flowing identically everywhere. Not a cosmic metronome detached from matter. Time is woven into space-time and responds to mass, energy and motion. That is profound and quietly humbling. Now think emotionally for a moment. We often speak of time as something that happens to us. We lose time, save time, waste time, spend time, run out of time. Human language treats it like currency or weather. Physics offers another view. Time is also relationship. Between events, between observers, between paths taken through reality. That does not solve deadlines, sadly, but it deepens perspective. Now PSR J1748-2446 AD also reminds us that speed and stability can coexist. Though time behaves differently near it, the pulsar's pulses can remain extraordinarily regular. This combination is beautiful. Extreme environment, reliable rhythm, distorted time, precise timing source. Nature enjoys such contrasts. Now let us compare scales again. On Earth, if you and a friend live at different elevations for years, tiny relativistic age differences accumulate. Minuscule, but real. Near a neutron star, differences accumulate much faster. The same laws apply. Only the volume of the lesson changes. This continuity is one of science's most reassuring features. The universe does not need separate rulebooks for ordinary and extraordinary places. It uses one framework across scales. T-cooling and pulsar timing do not involve equal complexity, but they share a lawful universe. Now imagine if early humans had known this. Campfires beneath stars, unaware that some distant points were compact remnants where time flowed differently. It took centuries of mathematics, experiment and observation to uncover that truth. Again, the universe was under no obligation to be intuitive. We learned anyway. That is worth admiring. There is another reason time near a spinning star matters scientifically. By measuring pulsar timing in binaries with exquisite precision, astronomers test relativity under strong field conditions. Some of the best confirmations of gravitational theory come not from giant machines on Earth alone, but from watching dead stars keep time. An ancient collapsed remnant can become a physics professor. Now let us rest briefly in the strange comfort of all this. Somewhere in a crowded globular cluster, a tiny star spins hundreds of times each second. Near it, time flows differently than it does here. Its pulses cross thousands of light years and reach instruments on Earth. We decode them while lying in beds, riding trains, washing dishes, or trying to fall asleep. Reality contains such juxtapositions constantly. The cosmic and the ordinary share the same evening. If time bends near such objects and gravity is immense, what happens to magnetism there? A refrigerator magnet can hold a shopping list. A compass needle turns toward Earth's magnetic field. An MRI scanner can peer into the body using carefully controlled magnetism. These are useful, familiar encounters with a force most of us rarely think about until it does something practical. We live among magnetic fields quietly. They guide migratory animals, help power cities, store information, drive motors, shape auroras, and occasionally hide on the side of the fridge behind a takeaway menu. So magnetism may feel domestic, manageable, ordinary. Then neutron stars arrive and politely ruin all proportion. PSR J1748-2446 AD is not only a compact object spinning around 716 times each second. Like many pulsars, it also carries an intense magnetic field. Perhaps not the most extreme in the known universe. That title belongs to magnetars and their truly outrageous fields, but still far beyond anything encountered in everyday human life. Enough to matter profoundly. Enough to shape radiation, particle motion, and the very identity of the pulsar. To understand why neutron stars are magnetic at all, let us go back to the star that existed before collapse. Many ordinary stars possess magnetic fields. They are generated or sustained through internal motions of charged plasma, rotation, and dynamo processes. The parent star of PSR J1748-2446 AD likely had its own magnetic structure. Then collapse occurred. The core shrank from stellar size to something city-sized, and when magnetic flux is compressed into a much smaller region, field strength can increase dramatically. Imagine drawing the same number of lines through a far smaller area. The concentration rises. What was once spread across a vast stellar body becomes packed into a compact remnant. The result can be extraordinary magnetism. A useful analogy is squeezing air into a bicycle pump, though fields are not air and analogies deserve supervision. Still, compression can intensify. So the neutron star inherits magnetism and amplifies it through collapse. Then rotation enters the story. A rapidly spinning magnetic object can accelerate charged particles around it. Those particles move along magnetic field lines, emitting radiation. This is one of the central reasons pulsars pulse. The beams we detect are tied to rotating magnetic geometry. Without strong magnetism, no classic lighthouse effect in the same way. So the magnetic field is not a side detail, it is part of the engine. Now let us speak about scale. Earth's magnetic field is gentle enough that you notice it mainly through instruments or compass behaviour. A bar magnet is stronger nearby but still entirely manageable. MRI machines generate powerful fields by human standards and require serious safety procedures. Neutron stars operate on another level entirely. Typical pulsar magnetic fields can be trillions of times stronger than Earth's field. Magnetars exceed even that by huge margins. Numbers that large can become abstract, so let us phrase it differently. Near such fields, atoms, electrons, and plasma behaviour can be altered in ways irrelevant on Earth. Radiation processes change. Matter organises differently. Charged particles are forced into tight motion along field lines. The environment becomes one where magnetism is not background, it is architecture. Now imagine trying to move freely near a strong neutron star magnetic pole as a charged particle. You would not be choosing your route. The field would choose it for you. Particles spiral along magnetic lines, accelerate, emit radiation, collide, generate pair cascades, and participate in a complex magnetosphere surrounding the star. This magnetosphere is a region dominated by magnetic forces and plasma interactions. That word, magnetosphere, may sound calm because Earth has one too. Ours shields us from solar wind and helps create auroras. A pulsar magnetosphere is a more intense relative. Same family name, very different temperament. Now let us return specifically to PSR J1748-2446 AD. Because it is a millisecond pulsar, its magnetic field is often thought to be lower than those of young ordinary pulsars, having evolved through long accretion history and aging. Yet, lower here is relative in the way a mountain can be lower than Everest, and still entirely a mountain. Even reduced pulsar fields remain immense by human standards, strong enough to guide particle flows, create emission zones, and sustain pulsar behaviour. So when we say this star is magnetic, we do not mean it can organise paperclips. We mean it structures a relativistic plasma environment around a city-sized collapsed star rotating hundreds of times each second. Context matters. There is another elegant feature of pulsar magnetism. The magnetic axis is often tilted relative to the rotation axis. That tilt creates sweeping beams. If the magnetic poles aligned perfectly with the spin axis, the lighthouse effect would be less dramatic observationally. But with tilt, the emission regions rotate through space like beams from a rotating lamp. Pulse after pulse reaches Earth if geometry favours us. So misalignment becomes visibility. A slight cosmic crookedness helps discovery. This happens often enough in life too. Now consider the energy involved. As pulsars rotate, they gradually lose rotational energy. Some of that energy powers electromagnetic emission and particle winds. The star slowly spins down over time, though recycled millisecond pulsars like PSR J1748-2446 AD can remain rapid for immense spans. In that sense, magnetism helps convert spin into signal. Rotation becomes radiation. Motion becomes message. There is something lovely about that transformation. Now, what would a strong magnetic field feel like to a person? That question is trickier than people expect. Humans do not directly feel static magnetic fields in the way we feel wind or heat, but extreme fields interacting with materials, electronics, charged particles, and biological systems would create severe practical consequences. Near a neutron star, survival problems from gravity and radiation arrive long before one conducts tasteful magnet experiments, so again, no tourism. But scientifically, such fields are priceless. They let us study plasma physics under extreme conditions, emission mechanisms, quantum electrodynamics in strong fields, and the behaviour of matter beyond laboratory limits. Neutron stars repeatedly do this. They take phenomena known on Earth and push them into regimes where theory must stretch. Gravity, density, rotation, magnetism, all intensified. Now, there is a subtle emotional comfort hidden here. We often imagine power as loudness. Large engines, bright lights, dramatic motion, visible force. Yet a magnetic field can be invisible and still dominant. It can shape trajectories, constrain particles, and define behaviour without spectacle. Invisible influence is common in reality. Gravity itself, air pressure, social norms, memory. Magnetic fields simply make the point physically. Now let's think about compasses. A compass aligns with Earth's field because magnetic torques orient the needle. Near a neutron star, the concept of a handheld compass becomes almost comically insufficient. The surrounding environment would overwhelm ordinary materials and instruments. This is not stronger fridge magnet territory. This is new regime territory. Sometimes the right response to scale is not comparison, but surrender. Now, because PSR J1748-2446 AD spins so quickly, its magnetic field is carried around rapidly as well. The magnetosphere co-rotates to significant distances until physical limits intervene. Electric fields arise naturally in such rotating magnetized systems, helping accelerate particles to high energies. So the pulsar is not merely a magnet, it is a rotating electromagnetic machine built by stellar collapse. Again, the phrase machine is metaphorical but useful. No designer, no workshop, no maintenance manual, yet functionally intricate. Now, if you listen to pulsar timing data, observe radio beams, or model pulse shapes, you're indirectly studying magnetic geometry. The pulse profile can reveal where emission occurs, how beams are shaped, and how the magnetic and spin axes are oriented. The lighthouse signal carries clues about invisible structure. That is one of science's favourite kinds of puzzle. Read the shadow, infer the object. Read the pulse, infer the field. There is another reason magnetic fields beyond comprehension matter for tonight's story. They help explain why PSR J1748-2446 AD is observable at all. Without a magnetic field guiding charged particles and producing beams, it might simply be a rapidly spinning compact star much harder to notice. Magnetism turns hidden spin into detectable rhythm. It makes speed visible. That is a generous service. Now imagine the broader scene. In a crowded ancient globular cluster, thousands of stars drift through long gravitational lives. Among them sits a tiny neutron star, spinning hundreds of times each second, wrapped in intense magnetism, sending pulses across the galaxy. Most nearby stars simply shine. This one announces there is something charming in that contrast. Now, once we appreciate the magnetic engine, another question naturally arrives. If pulsars are so regular, so rhythmic, and so dependable, could they be used as clocks? Could one of the strangest objects in the cosmos also be one of the most precise timekeepers known? If someone asked you to build the most accurate clock imaginable, you might not begin with an exploded star. You might choose polished metal, vacuum chambers, lasers, quartz crystals, atomic transitions, temperature control, carefully engineered electronics, and a room where everyone speaks softly near the instruments. All sensible choices. What you probably would not choose is a collapsed stellar core with crushing gravity, intense magnetism, and a habit of rotating hundreds of times each second in a crowded globular cluster. And yet nature did exactly that. Pulsars, including extraordinary objects like PSR J1748-2446 AD, are among the most precise natural clocks known. This is one of those facts that feels almost mischievous. The universe takes something violent in origin and turns it into something dependable in behaviour. A massive star lives fast. It collapses catastrophically. Its core becomes a neutron star. Then, ages later, it keeps time with astonishing regularity. From chaos comes cadence. Now, let us be clear. When scientists call pulsars clocks, they do not mean tiny clock faces appear on the surface with tasteful numerals. They mean the pulses emitted as the star rotates arrive with remarkable predictability. Each sweep of the beam marks another rotation. If the rotation is stable, the pulse train becomes a timekeeping signal. Tick, tick, tick. Except for PSR J1748-2446 AD, those ticks come hundreds of times per second. And unlike many human systems, the star is not late because of traffic. Why are pulsars so regular? Because neutron stars are compact, massive, and governed by simple rotational physics over long intervals. They have enormous inertia. That means they resist sudden changes in spin. A large spinning flywheel is harder to speed up or slow down than a toy top. A neutron star is the cosmic version of rotational stubbornness. Once rotating steadily, it tends to keep rotating steadily. This is conservation with attitude. Now combine that with the star's tiny size. A compact object has fewer floppy outer layers than a giant ordinary star. There is no broad gaseous envelope sloshing around in the same way. The structure is concentrated and stable. Rotation can therefore be extraordinarily consistent. That consistency becomes measurable from Earth through pulse timing. Astronomers record the arrival times of pulses and compare them to predictive models. Some pulsars are so regular that over certain intervals they rival atomic clocks in stability. Millisecond pulsars are especially prized because their fast spin provides many pulses and often excellent timing precision. This is one reason PSR J1748-2446 AD matters beyond speed. Fast spin gives more ticks to measure. More ticks mean more opportunities to detect tiny deviations, and tiny deviations are where science hides treasure. Suppose a pulsar were perfectly isolated in empty space with no complications. Its pulses would arrive according to its spin behaviour and gradual slowing over time. But real pulsars live richer lives. Some orbit companions, some move through the galaxy. Signals cross interstellar gas. Gravity bends paths. Motion changes timing. Each effect can slightly shift when pulses arrive. By measuring those shifts, astronomers learn remarkable things. A delay of microseconds can reveal orbital motion. A drift can reveal acceleration. A repeating wobble can reveal a companion star. Tiny irregularities can test relativity. The clock becomes an instrument panel. Now imagine hearing a metronome so precise that if one click arrives slightly early, you can infer the stage moved beneath it. That is pulsar timing in spirit. The regularity is so strong that deviations become information. This is why precision born from chaos is such a fitting phrase. The star's birth may have involved collapse, explosion, intense forces, and violent transformation. Yet the remnant can become calmer than the event that created it. Nature does this often. After storms, rivers run steadily. After volcanic upheaval, landscapes settle. After stellar catastrophe, pulsars keep time. There is comfort in that pattern. Now let us talk specifically about millisecond pulsars. These objects, often spun up by accretion from companion stars, can rotate hundreds of times each second with extraordinary stability. Because they are old systems that have undergone long evolutionary smoothing, many make superb clocks. PSR J1748-2446 AD rotating around 716 times per second, belongs to this distinguished family. Every second, hundreds of rotational markers become available. If the pulse beam geometry and signal quality cooperate, timing becomes exquisitely informative. Now, do pulsars remain perfectly constant forever? Not exactly. They gradually lose rotational energy and spin down over long timescales. Some young pulsars exhibit glitches, sudden small changes in spin rate thought to involve interior dynamics. Timing noise can occur. Environments can complicate signals. So perfect clocks is affectionate shorthand, not literal flawlessness. But compared with many natural systems, they are astonishingly stable. And importantly, their imperfections are often scientifically valuable. A glitch can reveal superfluid interiors. Orbital timing shifts reveal companions. Propagation changes reveal interstellar plasma. Even irregularity becomes data. That is one of science's happiest habits. Nothing wasted. Now let us widen the lens. Astronomers use arrays of millisecond pulsars spread across the sky as a kind of galactic observatory. By timing many pulsars over years, they can search for correlated distortions caused by passing gravitational waves from supermassive black hole binaries and other cosmic sources. Think about that carefully. We use distant collapsed stars as synchronized clocks to detect ripples in space-time. If this sounds like fiction, it is because reality occasionally refuses to be modest. The galaxy itself becomes an instrument, each pulsar a timing node, humanity listening across years. This should inspire admiration. Now return to Earth for a moment. Our daily clocks require batteries, springs, power grids, charging cables, or at minimum someone remembering where they were placed. They drift, fail, reset after outages, or blink 0000 in silent accusation. A pulsar needs none of that. It requires no winding, no software update, no user agreement. It simply obeys physics. There is something refreshing in that. Now one might ask, if pulsars are so good, why not use them for everyday wristwatches? Several reasons. Distance is inconvenient. Signal collection requires radio telescopes rather than wrists, and local time zones remain annoyingly terrestrial. Still, spacecraft navigation using pulsars has been explored. Autonomous deep space navigation by timing known pulsars is a serious concept. If GPS uses satellites around Earth, future explorers might use stars around the galaxy. Your destination may someday depend on a dead star's punctuality. Now that is a sentence worth keeping. There is also philosophical charm here. Humans invented clocks partly because we crave order. We coordinate meetings, seasons, prayer, farming, trains, and sleep. Timekeeping is civilization trying to agree with itself. Pulsars reveal that order was already present in the cosmos. Long before clocks on towers, neutron stars rotated steadily. Long before calendars, orbital rhythms marked years. Long before schedules, nature kept count. We did not invent rhythm. We joined it. Now let us think emotionally about reliability. Reliable things calm us. A friend who arrives, a heartbeat in range, a train that usually means what it says, rain at night repeating softly, predictable pulses from a star thousands of light years away. Regularity lowers cognitive load. The mind rests when patterns hold. Perhaps that is one reason pulsars feel satisfying even to non-specialists. They are remote examples of dependable order in a complicated universe. Now, PSR J1748-2446 AD is especially striking because the same object can be described in two opposite ways, and both are true. It is one of the fastest spinning known neutron stars. It is one of nature's most stable clocks, fast and steady, extreme and precise, violent in origin, disciplined in present behaviour. Reality often contains such pairings. Now imagine a listener lying quietly tonight while somewhere in Terzan 5 this pulsar completes hundreds of rotations each second. Each turn contributes to a rhythm older than nations, steadier than moods, indifferent to calendars. That can feel strangely reassuring. The day may have been messy. The universe still contains clocks. How exactly do astronomers study these rhythms in practice? How do they listen, measure, and turn faint pulses into knowledge about stars, gravity, and the galaxy itself? Long before humanity could explain the stars, we listened for patterns, footsteps in the dark, rain on roofs, waves returning to shore, birdsong at dawn, a heartbeat through a stethoscope. We are a species unusually responsive to rhythm. Repetition catches attention. Irregularity raises concern. Tempo can soothe, alarm, guide, coordinate, and reveal hidden structure. So perhaps it was inevitable that once we built the right instruments, we would begin listening to the sky in the same way. Not with ears alone, of course, with telescopes, receivers, clocks, mathematics, and patience. That is how astronomers listen to pulsars, the universe's most disciplined heartbeats. PSR J1748-2446 AD, spinning around 716 times each second, is one such rhythm source. A tiny neutron star in a dense globular cluster sends repeated signals across thousands of light years. Those signals are faint by the time they reach Earth. Yet with enough care we can detect them, measure them, and learn from them. This is one of the grand achievements of modern science. We built tools delicate enough to hear a city-sized star turning in the dark. Now let us begin with radio telescopes. Many pulsars are first detected through radio emission. A radio telescope does not see invisible light. Instead, it collects radio waves, electromagnetic radiation at longer wavelengths than light our eyes detect. Some radio telescopes are giant single dishes. Some are arrays of many antennas working together. Some stare at one patch of sky. Some survey wide regions. Whatever the design, the basic goal is the same: gather weak signals from space and separate meaning from noise. That phrase, noise, matters. Earth is loud in radio terms. Phones, satellites, electronics, aircraft systems, transmitters, natural atmospheric effects, and countless human technologies create interference. The sky itself also contains many radio sources: galaxies, gas clouds, the sun, background emission. Finding a pulsar signal among all that is not unlike hearing one metronome in a city full of machinery. And if the pulsar is fast, faint, or distant, the challenge grows. PSR J1748-2446 AD is all the more impressive because its pulses come hundreds of times each second. Detecting such rapid regularity requires precision timing and careful analysis. Now imagine what the telescope receives. Not a tidy label saying, "Oh, hello, fastest spinner here." It receives streams of changing electrical data produced when incoming radio waves interact with detectors. Those streams must be processed, cleaned, corrected, and searched. Astronomers then use algorithms to look for periodic signals. Does a pattern repeat every certain number of milliseconds? Does it persist over multiple observations? Could it be interference from Earth instead? Does it shift because the pulsar is in a binary orbit? Each candidate must be tested. Discovery is often less dramatic than films suggest. More spreadsheets, more statistics, still glorious. Now there is another obstacle between us and pulsars: interstellar space. Space is not empty in the absolute sense. It contains thin gas and plasma. Radio waves travelling through this material experience dispersion. Lower frequencies are delayed slightly more than higher frequencies, so a sharp pulse emitted by the pulsar can arrive smeared across frequencies. Fortunately, physics is kind enough to be consistent. By measuring this effect, astronomers can correct for it, a process called de-dispersion. The pulse becomes sharper again. In doing so, researchers not only recover the signal, but also learn something about the amount of material the waves crossed. Even the distortion carries information. That is one of science's favourite outcomes. Now let us move from discovery to timing. Once a pulsar is known, astronomers observe it repeatedly and record pulse arrival times with extraordinary accuracy. They compare the observed arrivals with a predictive model including spin rate, spin down, position in space, orbital motion if present, Earth's motion around the Sun, relativistic effects, and signal travel corrections. This is delicate work. If the model predicts a pulse at one instant and it arrives slightly early or late, that residual difference may reveal something real. Perhaps the pulsar moved in orbit, perhaps interstellar plasma changed, perhaps the telescope clock needs correction, perhaps gravity along the path altered timing, perhaps a companion object tugs the pulsar. Tiny mismatches become clues. That is why pulsars are so valuable. Their regularity creates a clean baseline against which subtle effects become visible. Now consider PSR J1748-2446 AD in particular. Because it spins so rapidly, it offers many pulses per second. Hundreds of timing markers arrive each second. That can be advantageous for precision if signal quality is sufficient. The star effectively provides a rapid stream of timestamps generated by nature itself, a cosmic clock with excellent work ethic. Now, why call these heartbeats? Partly metaphor, partly pattern. A heartbeat is rhythmic, meaningful, and diagnostic. Doctors learn much from timing, regularity, pauses, accelerations, murmurs. Pulsars are similar in spirit. Their pulse patterns reveal internal and external conditions. Stable rhythms suggest one story. Sudden glitches suggest another. Orbital modulation tells of companions. Changes in dispersion reveal intervening plasma. The pulse is both signal and symptom. That metaphor helps the mind feel the science. Now let us talk about arrays. Some of the most ambitious pulsar projects time many millisecond pulsars spread across the sky. These collections are called pulsar timing arrays. By monitoring numerous ultra-stable pulsars over years, astronomers search for correlated timing changes caused by gravitational waves passing through space-time. Imagine many clocks distributed across the galaxy. If space-time gently stretches and squeezes, their pulse arrivals shift in characteristic ways. This is breathtakingly clever. Use dead stars to detect ripples caused by giant black holes. If someone had proposed it casually centuries ago, they might have been asked to rest. Now it is real science. There is also the human side of listening worth honouring. Behind every pulsar measurement are engineers building receivers, technicians maintaining instruments, software developers refining pipelines, students checking anomalies, observers scheduling telescope time, analysts fitting models, and researchers arguing productively over interpretations. A pulse arrival time may look like one neat number in a paper. Behind it stands a community. Precision is social as well as technical. That is true in many fields. Now imagine the emotional contrast. A person on Earth sits at a console late at night. Monitors glow softly. Data streams in from a telescope. Somewhere far away in Terzan 5, PSR J1748-2446 AD keeps rotating. Its pulses began travelling before some trees now living had sprouted. They arrive now as tiny fluctuations in receivers. Distance collapses into measurement. Time collapses into timestamp. This is one of the quiet miracles of science. Now, do astronomers literally listen with speakers? Sometimes yes, in sonification or diagnostic contexts. Converting signals to audio can reveal patterns and help public understanding, but most listening is metaphorical. Reading data streams, timing residuals, spectra, folded pulse profiles. Still, the metaphor endures because it is accurate in spirit. We are attending to rhythm. We are hearing with mathematics. Now there is another challenge. Earth itself moves. Our planet rotates and orbits the Sun. The solar system moves too. If you want exquisite pulse timing, you must account for observer motion. Astronomers often convert arrival times to what they would be at the solar system barycenter, the centre of mass of the solar system. Even to listen well, one must know where one stands. That feels useful beyond astronomy. Perspective matters, motion matters, reference frames matter. Now let us pause on humility. For most of history, pulsars were unknown. The signals crossed space unnoticed. Then in the 20th century, with radio astronomy and improved instruments, they entered human awareness. The universe had not changed. Our ability to listen had. Many discoveries follow this pattern. Truth waits patiently. Tools catch up later. Now PSR J1748-2446 AD continues to turn regardless of whether anyone is observing tonight. It does not perform for telescopes. It does not seek headlines. It simply exists under laws of nature, generating rhythm through spin and magnetism. There is something restful in that indifference. Reliable things need no audience. Now another question naturally rises once we understand how carefully astronomers listen. What have these heartbeats taught us that we still do not fully understand? After everything we have learned about neutron stars, pulsars, gravity, dense matter, magnetic fields, and the astonishing speed of PSR J1748-2446 AD, it would be tempting to imagine the case is nearly closed. We found the object. We measured the spin. We understand the broad life story. We know it is a neutron star in a binary-rich environment. We can model its pulses. We can place it within stellar evolution. Surely the mystery is mostly solved. And yet, some of the most interesting parts begin exactly here, because science is often like standing in a room after turning on one lamp and discovering 5 more doors. PSR J1748-2446 AD is not only an answer, it is a question machine. The same is true of neutron stars generally. They are among the best studied extreme objects in astronomy, and among the least completely understood in detail. We know enough to be amazed responsibly. We do not know enough to become complacent. That is a healthy place for knowledge to live. Now, let us begin with the deepest question. What exactly is inside a neutron star core? We know outer layers better than inner ones. The crust can be modelled with increasing confidence. Densities there, while extreme, remain closer to nuclear regimes we can partially connect to laboratory physics. But deeper down, pressure rises to levels impossible to reproduce fully on Earth. Matter may transform into states we cannot yet confirm directly. Do neutrons remain the dominant identity all the way inward? Do hyperons appear, particles containing strange quarks? Do meson condensates form? Does matter dissolve into deconfined quark soup? Are there mixed phases layered in ways not yet fully captured? Or does reality choose an option not neatly listed in textbooks? We do not yet know. This uncertainty is not failure, it is frontier. Now consider why PSR J1748-2446 AD matters here. Because its extreme spin places constraints on possible internal matter behaviour. A neutron star rotating around 716 times per second must remain structurally stable. Some equations of state, descriptions of how dense matter responds to pressure, fit that requirement better than others, so every fast pulsar narrows the menu. Still, narrowing is not the same as solving. Nature often answers in hints first. Now let us ask another obvious question. Why is this the fastest confirmed spinner we know? Is 716 Hz near nature's preferred ceiling, or merely near the current observational ceiling? Could faster neutron stars exist, hidden by weak beams, unfavourable geometry, signal smearing in binaries, or limitations of surveys? That possibility remains open. The universe has a habit of containing things just beyond our instruments. History advises humility. There may be a faster pulsar already spinning tonight, unnoticed in some distant cluster or obscured region of the galaxy. Or perhaps spin-up processes truly stall near this range for common neutron star masses and magnetic histories. We are still learning. Now let us talk about braking mechanisms. If accretion from a companion can spin a neutron star up, what stops it from continuing indefinitely until breakup? We discuss several candidates: magnetic torques, reduced mass transfer, structural limits, gravitational wave emission, internal oscillations, but which dominates in real systems and under what conditions? That remains an active area of research. Some neutron stars may be held back by one mechanism, others by another. Nature rarely chooses one universal personality when several are available. Now consider the magnetic field. We know pulsars are magnetized. We know fields shape beams and particle acceleration, but exactly how and where radio emission is produced in the magnetosphere is still not completely settled in every detail. Different models place emission zones at different altitudes or regions relative to magnetic poles and outer magnetosphere structure. How do plasma cascades organize? Why do pulse profiles vary as they do? Why do some pulsars switch states or modes? How does long-term magnetic evolution proceed in recycled millisecond pulsars? Again, many clues, few final answers. Now let us move inward once more. Superfluidity inside neutron stars is strongly suspected. In some regions, neutrons may behave as a superfluid, flowing without ordinary viscosity. Protons may become superconducting under certain conditions. If so, the interior is stranger than most science fiction manages on weekdays. But how exactly are these phases distributed? How do vortices in a rotating superfluid pin and unpin? How do they contribute to glitches, sudden changes in spin observed in some pulsars? What coupling exists between crust and core? These are difficult, fascinating questions. A spinning star may hide quantum fluids the size of cities. Now there is the issue of mass and radius. For neutron stars generally, precise simultaneous measurements of both are precious, because they constrain dense matter theories. But such measurements are challenging. Different methods rely on X-ray modelling, pulse profiles, binary dynamics, cooling behaviour, and other techniques. Each comes with uncertainties. Science advances not by pretending uncertainty away, but by quantifying it carefully. That discipline is one reason progress is trustworthy. Now let us speak of time. Pulsars are clocks, yes, but some exhibit timing noise, small irregular wanderings not fully predictable. What causes every form of timing noise? Magnetospheric changes, internal dynamics, external torques, likely multiple causes. Again, one symptom, several pathways. PSRJ 1748-2446 AD itself, through continued monitoring, may help refine broader understanding of millisecond pulsar timing behaviour. Now, another frontier, gravitational waves. Could rapidly spinning neutron stars emit continuous gravitational waves if they possess tiny asymmetries? In principle, yes. Detecting such signals would reveal internal structure and deformations directly. But the signals are subtle. Current detectors continue improving. A future detection from a fast pulsar would be extraordinary. Imagine learning the shape of a distant neutron star from ripples in space-time. Reality permits elegant ambitions. Now let us not forget formation history. We have a plausible narrative for PSRJ 1748-2446 AD, birth in stellar collapse, later recycling via binary accretion in dense Terzan 5. But the exact sequence may be more complex. Was the current companion the original companion? Did exchange interactions in the globular cluster alter the binary? How much mass was transferred? Over what timescale? What was the star's initial spin and magnetic field? Ancient systems rarely preserve tidy diaries. We reconstruct from clues. Now there is a broader philosophical point worth resting with. People sometimes imagine science as a machine that converts mystery into certainty until nothing interesting remains. The opposite is closer to true. Good answers reveal better questions. We discovered atoms and opened quantum theory. We explained stars and opened nuclear astrophysics. We found pulsars and opened dense matter, precision gravity tests, plasma mysteries, and timing arrays. Knowledge does not end wonder. It refines it. PSR J1748-2446 AD is a perfect example. At first glance, it is the star that spins 700 times every second. That headline is already delightful. Then you look closer. What is inside it? Why exactly that speed? How stable can matter be? What unseen torques act? What does its cluster history hide? Could faster cousins exist? The simple fact becomes a doorway. Now consider the emotional usefulness of frontier science. It reminds us that not knowing is not emptiness. It is structure awaiting discovery. There are disciplined ways to be uncertain. There are productive ways to ask questions. That matters beyond astrophysics. Many parts of life resist final certainty. We can still proceed carefully, honestly, curiously. Science models that well. Now let us imagine future instruments, more sensitive radio arrays, better X-ray timing missions, improved gravitational wave detectors, sharper computational models, longer pulsar timing baselines. With these tools, PSR J1748-2446 AD may yield new constraints decades after its discovery. Some objects continue teaching long after headlines fade. Quiet teachers often do. There is also humility in the fact that a city-sized remnant star in a crowded cluster can challenge our best nuclear theories. We build colliders, satellites, observatories, and supercomputers, yet nature casually maintains environments beyond our direct replication. The cosmos remains ahead in infrastructure. Why does any of this move us at all? Why do humans care that a tiny star spins hundreds of times each second in a distant cluster? Most of the universe does its work quietly. Stars fuse hydrogen without applause. Galaxies rotate without announcement. Planets circle their suns without issuing progress reports. Black holes distort space-time with no interest in publicity. Even comets, those theatrical visitors with tails and flair, spend much of their existence in cold darkness minding long, elliptical business. We humans, by contrast, are rather noisy creatures. We narrate breakfast. We review weather. We argue over parking. We create alerts for things that could have remained thoughts. So there is something calming about realizing that reality itself is often silent while still immensely active. PSR J1748-2446 AD is a beautiful example. Somewhere in the globular cluster, Terzan 5, hidden among countless stars, a neutron star smaller than a city spins around 716 times every second. It has likely done so for ages. It pulses beams through space. It obeys gravity, magnetism, and quantum laws under conditions far beyond everyday imagination. And it does all of this without ceremony. No fanfare, no visible panic, no need to be noticed. The star simply turns. That image can settle the mind. We often associate importance with noise. The louder the event, the more significant it must be. Yet many of the largest processes in existence are nearly silent to human senses. Continents drift slowly. Seasons tilt in and out. Cells divide. Forests grow ring by ring. Time changes faces gently. Galaxies wheel over hundreds of millions of years. Significance and volume are poor synonyms. Now let us consider spin itself. Rotation is one of the universe's favourite habits. Earth spins. The moon once spun differently and became tidally shaped. Planets rotate, stars rotate, accretion disks whirl, galaxies turn in broad, majestic patterns. Even storms form spirals when conditions allow. Why so much spinning? Because when clouds collapse, matter falls inward, and systems evolve, angular momentum tends to remain in the story. The universe is reluctant to waste motion. Small initial turns can become rapid rotation when material contracts. We saw this with PSR J1748-2446 AD. A larger star became a compact remnant. Spin intensified. Then perhaps a companion star helped accelerate it further. So this tiny neutron star is not an isolated oddity. It is part of a grand rotational tradition. The cosmos likes circles, orbits, whirls, cycles, turns within turns. There is comfort in recurring structure. Now imagine the silence again. If you stood in ordinary space near such a star, setting aside the many reasons that would be your final scheduling error, you would not hear mechanical whirring in air. Space does not carry sound the way Earth's atmosphere does. The spin is physically real, yet acoustically absent. Motion without noise. Energy without soundtrack. We are used to engines that roar and wheels that hum. Human machines announce themselves. Cosmic machinery often does not. That contrast is striking. A neutron star rotating hundreds of times each second may be quieter to ears than a refrigerator. Reality has a sense of irony. Of course, we can translate pulsar signals into sound, and we do. We make tones, clicks, rhythms, audible renderings. But these are acts of interpretation, ways of bringing hidden patterns into sensory reach. That matters because many truths are silent until translated. Radio waves need receivers, numbers need context, emotions need language, stars need telescopes. Now, why does silent spinning feel meaningful? Perhaps because it reveals a world that continues independent of our attention. There is something steadying in that. While human schedules rush and stumble, while headlines flare and vanish, while inboxes multiply with unsettling confidence, distant systems continue their lawful motions. Earth rotates tonight, the Moon orbits, Jupiter turns, PSR J1748-2446 AD spins hundreds of times each second. None of these processes wait for permission. This can feel small-making, but also relieving. Not everything depends on us. Now let us think about patience. That pulsar did not become what it is instantly. A star formed. It lived. It exhausted fuel. It collapsed. It likely entered a binary history involving accretion and spin-up. It aged. It settled into present behavior. Long story, quiet, present. Many things work this way. Trees spend years becoming shade. Craftspeople spend years becoming effortless looking. Friendships become deep gradually. Stars become clocks over ages. We often witness finished states and forget hidden timelines. PSR J1748-2446 AD reminds us to respect preparation. Now there is another silence worth noticing. Informational silence. For most of human history, this star existed unknown. It pulsed through space unnoticed by every empire, language, dynasty, market, poem and worry. The signals crossed darkness, while humanity invented agriculture, geometry, shipping lanes, clocks, electricity, radio, and finally the tools to detect them. The star was not newly active when discovered. We were newly capable. That distinction is profound. Many realities are present before awareness arrives. Science often changes not the universe, but our relationship to it. Now imagine lying awake at night feeling that nothing is moving forward. A common human sensation. Yet outside, movement is constant. Blood circulates. Clouds shift. Tectonic plates creep. Planets spin. Stars orbit the galactic center. A neutron star in Terzan 5 completes hundreds of turns before you finish reconsidering an awkward conversation from 2018. Perspective can be medicinal. Now silence should not be mistaken for emptiness. A quiet room may contain thought. A still lake may contain depth. Dark space may contain pulsars, fields, dust, radiation, and histories beyond counting. Likewise, a silent star can contain some of the most extreme matter in the universe. Surface calm often hides structural intensity. Again, a useful lesson. Now, let us return to rhythm. The pulses of a pulsar are regular enough to be clocks. We detect them because the star's magnetic beam sweeps our direction. That means even silence has cadence when properly observed. The universe may not shout, it often taps, repeatedly, with exquisite timing. There is something almost intimate about that. Across thousands of light years, a compact remnant keeps sending measurable beats, not for us specifically, but available to us once we learn how to listen. Many forms of meaning are like that, not addressed personally, still available. Now think of Terzan 5 itself, crowded and ancient. Thousands upon thousands of stars share that cluster. Among them, our speed record holder turns almost invisibly. No neighbouring stars gather to celebrate. No cluster newsletter announces monthly rankings. Most greatness in the cosmos is unrecognised locally. This too may comfort ambitious minds. Recognition is not the same as reality. Now we might ask whether silence makes the universe lonely. I do not think so. Silence can also mean spaciousness, room enough for thought, room enough for pattern, room enough for delicate signals to cross immense distances without being drowned. If space were filled with atmospheric noise, radio astronomy would be far less charming. The hush is part of the gift. Now there is one more subtle point. We humans create clocks because time feels slippery. The universe creates pulsars because physics allows consequences. Yet those consequences become clocks for us. Meaning can emerge from systems not designed for meaning. That is true far beyond astronomy. Rain was not made to soothe you. Trees were not made to inspire painters. Pulsars were not made to teach relativity. Yet they do. Now somewhere tonight, while rooms dim and streets quiet and many people drift towards sleep, PSR J1748-2446 AD continues turning, hundreds of rotations each second. No strain visible from afar, no complaint, no applause, just continuity, just law, just motion sustained across ages. That can be enough to steady the mind. And after travelling through dense matter, strong gravity, magnetism, time dilation, binary companionship, and silent cosmic rhythm, one final step remains. We should return home with the question that began all this wonder. What does a distant spinning star change in us once we know it exists? Here, at the end of our journey, the room is likely quieter than when we began. Perhaps the lights are low. Perhaps the day has loosened its grip a little. Perhaps you are listening from bed, from a sofa, from a train seat, from somewhere between wakefulness and sleep. Perhaps you're in a city full of windows, or somewhere rural where darkness still feels properly dark. Wherever you are, thank you for bringing your attention here for a while. Tonight we followed the story of PSR J1748-2446 AD, a neutron star smaller than a city that spins around 716 times every second. We began with a number, we ended with perspective. Along the way we passed through stellar collapse, matter compressed beyond ordinary imagination, magnetic fields of astonishing strength, clocks more precise than intuition expects, gravity strong enough to bend light and alter time, and a crowded ancient cluster where this tiny remnant continues its rapid turning. That is a lot for one object. The universe is often efficient with wonder. Now let us gently ask the simplest question. What does this have to do with you? On one level, nothing at all. The star does not know your name. It does not adjust its spin to your mood. It is not sending personal messages hidden in pulse timing. If it were, they would be extremely repetitive. The cosmos is not centered on us. That truth can feel cold if stated carelessly, but there is another way to receive it. If the universe is not centered on us, then we are free to belong to it rather than carry it. That is lighter. You do not need to hold the sky together. You do not need to keep galaxies aligned. You do not need to solve existence before breakfast. Large systems are already in motion. Earth rotates without supervision. The moon keeps orbiting. Stars are born and die on schedule entirely their own. PSR J1748-2446 AD spins hundreds of times each second whether or not anyone is anxious. There can be relief in that. Now think about rhythm. Your day likely contained many rhythms already. Breathing, walking, speech, notifications perhaps more than necessary, traffic lights, meals, thoughts returning in loops, tension rising and easing. The body itself is layered with rhythms, heartbeat, sleep cycles, hormones, blinking, attention drifting and returning. Life is patterned even when it feels messy. The cosmos is patterned too. Planetary orbits, tides, seasons, solar cycles, galactic turns, pulsar beats crossing space. You are not outside rhythm looking in. You are one rhythm among many. That idea can soften loneliness. Now let us consider scale, because scale can intimidate people. A star thousands of light years away, spinning in an ancient cluster, may seem to make human life tiny. And yes, compared with cosmic distances, we are small. But small is not the same as insignificant. A seed is small. A note in music is small. A cell is small. A sentence can be small and still change someone's life. Scale measures size, not meaning. This matters greatly. The universe contains enormous empty regions and still values precision. Pulsars prove that. A tiny object can become one of nature's finest clocks. Compact things can matter immensely. You too need not be vast to matter. Now think about time. We learned tonight that near massive objects, time itself can pass differently. Clocks disagree depending on gravity and motion. Even this familiar thing we call time turns out to be more flexible than it first appears. Perhaps that can remind us to be humble with our own clocks. We measure days, deadlines, birthdays, delays, progress, age. Necessary tools, yes, but not always the full story. A difficult week can feel long. A joyful hour can vanish. Waiting stretches minutes. Wonder compresses them. Human time has texture. Physics has equations. Both are real in their own ways. Now think about change. PSR J1748-2446 AD was not born a record holder. It was shaped through stages: formation, collapse, partnership, transfer, acceleration, persistence. Its present state is the result of many earlier chapters hidden from direct view. Most meaningful things are like that. People too. No one sees the full process behind steadiness, skill, kindness, resilience, or recovery. We often compare our unfinished middle to someone else's visible outcome. The star would advise patience if stars gave advice. They do not. Still, the lesson stands. Now let's return to silence. Much of the universe works quietly. That can be comforting in an age where noise often impersonates importance. Your most important growth may also be quiet. Healing can be quiet. Learning can be quiet. Choosing better patterns can be quiet. Rest itself is quiet. Do not underestimate silent progress. The cosmos certainly does not. Now perhaps you are feeling sleepy. If so, excellent. Science has once again served civilization in a noble secondary role. If not, that is all right too. Rest does not always begin with sleep. Sometimes it begins with perspective. Sometimes it begins with noticing that your current worry exists inside a universe where neutron stars spin in ancient clusters and galaxies turn slowly through darkness. Problems remain real. They are simply not the whole frame. Now imagine, just for a moment, the ongoing scene beyond your walls. Clouds moving somewhere, oceans shifting, cities glowing, forests breathing, the Earth rotating beneath you, the solar system travelling through the Milky Way, and in Terzan 5, PSR J1748-2446 AD, completing hundreds of rotations this second, then hundreds more the next. Motion everywhere, continuity everywhere. You're already inside the dance. There is no need to earn entry. Now let your breathing join the larger pattern. In, out. No need to force it. No need to optimize it. Just one more rhythm in a rhythmic universe. If thoughts arrive, let them pass like signals crossing distance. If worries appear, let them be small weather, not permanent climate. If sleep comes, welcome it without ceremony. The stars are not grading your relaxation. Now, before we part, thank you for spending this time with Science for Sleep. If this brought you calm, curiosity, or a gentler end to the day, you're always welcome back. There will always be more strange corners of reality to explore softly together. And while you rest tonight, the universe will keep its many clocks. The Earth will turn, the sky will move, the distant pulsar will spin, and somewhere within all that motion, you have your own place in the rhythm of the cosmos,